Good morning, besides Orlando. Is it anybody's first time besides Orlando? First besides Orlando. All right. Thank you very much for coming down to track 2. Anybody here in the room did SOC before or is currently doing SOC kind of work? Yeah, a little bit. All right. Anybody here did some investigations, was part of a breach? Okay. All right. So let's start with a story. Assume you are responding to a breach and you're thinking in your mind, what could have went better? Well, usually most people would start blaming essentially their investigation. They would start blaming, I should have had an idea of what's going on with my logs, what went on with my incident a lot earlier. And usually the problem would be I didn't really find the alerts that were part of this essentially attack. And that's why I kind of missed this breach. I wonder, does anybody here know why do we have one alert at a time in our queues in the SOC? Why do we usually look at one alert at a time or one log at a time? Yes. Fair. But why are we not looking at groups of logs? Like if you right now go to YouTube, are you going to generate one log? You're gonna generate like 700 net flows, 500 Windows event logs, and 3 million packets in TCP and UDP. So why do we look at one log if literally one activity online generates thousands of logs? What is the point of utilizing a log as a unit? Why is the unit not thousands of logs? Like, we know that if I go to YouTube, that's a unit of an activity, right? Like, I went to YouTube for a few minutes, but that does not translate into logs. That translates into a correlation that someone has to do, right? Like, someone has to actually figure out thousands of logs that represent a story of a few words that I went to YouTube for a few seconds. Well, I wonder if we look at alerts one at a time because we're always thinking about maybe cybersecurity and cyber attacks, and maybe going to YouTube generates a lot of logs, but maybe an attack doesn't really generate a lot of logs. Maybe there's always like this one log that would matter a lot. Well, in reality, attacks are very, very essentially rare as part of your data. Anybody here collects more than 1 terabyte in their SOC a day? More than 1 terabyte? How many terabytes a day? 12 or 13 terabytes a day? What kind of SIM, like Splunk? Fair. So why are we ingesting 12 terabytes, in this case, worth of logs into Splunk? Just to get you the numbers, 12 terabytes a day into Splunk, that's like $12 million essentially a year. So if you talk to any CISO, any decision maker, any CTO, any CIO, and you tell them, what is the biggest cybersecurity budget item that you have? They're going to be like, the SIM. $12 million. Like, imagine how many people you can hire. Like, assume a position is like 6 figures, and assume you can like save even half of that 12 million. You can hire 60 people. Like 60 people. You can hire like a few departments in cybersecurity. If you can reduce the bloat of that data for a little bit. And in reality, anybody here in the SOC does correlations or investigations of these logs? Or is it always like one log at a time? Like right now, if you take me to your SOC and I'm gonna look at your queue of logs and queue of alerts that we should look at, am I gonna see one alert at a time, or am I gonna see a correlated group for each case? One at a time? Group? What do you think? You'll see a bunch at a time. How do you group these bunch? Right. Okay. Is that like a service provider, like in this case? Right. Is it a managed SIM or is it like okay, someone is managing? Okay. All right. How do you think they're making these groupings? Like, what goes in their mind to build these groupings for you? Okay. Okay. So, if you were to look at the groupings, they would essentially be based on a human that put them together or based on rules that were put together? Based on rules. So, someone created rules, we call them, I think, correlation rules, right? And these correlation rules are so good, they were able to essentially group things. You might think this is how we do it in big data. Do you use other big data in your life other than cybersecurity? Like, do you use YouTube, MySpace, Instagram? These are a lot bigger data platforms, right? 12 terabyte is no more happening a day. 12 terabyte is happening like every second of ingestion, right? So with these big data, like real big data platforms, you think they have correlation rules? You think I can go to YouTube and be like, if something matches this correlation rule, add it in a playlist? No. If I go to YouTube, I'm gonna already see a bunch of stuff that is correlated automatically to my account and things that I like. Right? If I go to Instagram, it's gonna already have that. No one has me writing correlation rules other than cybersecurity. Right? They just figured out correlation because it's not that big of a deal anyways. Like they figure it out for you. And they still give you the search engine, they still give you a little search bar at the top, but it's not really the main part of how do we use YouTube. It's not really the main part of how do we use Instagram. It's not really the main part of how do we interact with the big data. Not through the search bar, mainly through the feed. No one goes to their feed on Twitter or LinkedIn or whatever and has a problem with correlation. This problem with correlation, this idea of, oh my God, correlating data is so hard, is literally just made up in cybersecurity. And we don't really have that much of a big data. And our data is not that hard or full of metadata similar to maybe YouTube's videos. Our data is smaller, easier, actually more standardized, and our data is not that big. 12 terabytes is not that big. Yet, we are spending $12 million. You think YouTube would run on $12 million worth of infrastructure to give you a bunch of recommendations of what you should be looking at when you first open the app? No way. So, what is so special about cybersecurity data for people that work in the SOC and essentially work on correlation rules, but at the same time they still use their phone and they go to YouTube and everything is already correlated for them? Why do you think there is a problem with correlation in cybersecurity? Why is it so special?
I'll say a lot of the different tools and the formatting of the data and the unique identifiers to be able to track it back to one thing can be painful.
You don't think YouTube pinpoints the upload back to a user and looks at the fraud of the user and looks at the fraud of the bots doing likes and comments and views, and they're looking at ads, they're looking at so many things. Why is our data harder? They're considering a million more things. And they do the correlation without $12 million worth of stuff for 12 terabytes. Their compute, their infrastructure, their storage, their networking is a lot cheaper.
It's a lack of context.
Lack of context.
Because you get all this information into a SOC, and you don't, if it's dissimilar, you don't have an idea of what matters to you right away. You have to kind of piece out each piece.
Why? How come Instagram knows what's relevant? How come LinkedIn knows what's relevant? How come YouTube knows what's relevant?
Because
Why doesn't Splunk know what's relevant?
we've trained it. We've trained the
So why don't we train Splunk? Splunk is a lot more expensive than the ad revenue coming out of Elastic. Well, let's not pick on Splunk. Elastic, Azure Sentinel, whatever. Why is this idea of let me interact with my big data so different on literally any application on this phone, which has absolutely no buttons and no keyboard, because no one freaking uses the search bar anymore? You just open an app and it immediately tells you what you should be looking at. But then you go to Splunk or you go to any SIM, Azure Sentinel, whatever, and there are no recommendations. There is always a big search bar and that's it. And it's on you to write the correlation rules if you would like correlation. Because correlation is so hard and so manual and such a big deal. Why? Why? Yes. I mean, YouTube still has a model feedback, right? You can say yes, good recommendation, bad recommendation. Same goes on Amazon, Netflix. Good next suggestion, bad next suggestion. Why doesn't Splunk just tell you, here's the grouping, and you say good grouping, bad grouping, or Sentinel or whatever other sim, good, bad? Why do I have to go and build quote correlation rules for big data and make a whole platform around it and pay this much compute and infrastructure? Like, how are these companies profitable? How do you think YouTube is profitable? 12 terabytes, they look at it in like a second at this point. That's not really that big of a data. But they don't spend that much money on it. They don't spend that much effort on it. They don't talk about correlating it. They have a recommender system that correlates things since the 60s, and it has been working for literally every app and website in the world. Even MySpace, when I was a little kid, would tell you what account is similar to what account. Every single feed, every single RSS feed knew what content is relevant to what content. But we look at logs. Oh no, nobody knows what's relevant to what. Like, oh no, that's special. Like, that's so hard to know. Like, why? Sorry, there was a hand up there. Yes.
Say we want to build a type of application or platform that their data is consistent, so they can build their algorithms using machine learning or other things.
Consistent in terms of format,
Consistent, yeah.
like the schema.
Yes.
Really?
Or in certain parts of data that's especially
You can upload so many different data types to Facebook though. Like my feed would have videos, reels, shorts, marketplace listings. There's so many different data types. And then I look at my Splunk and the only data types are like log, alert, event, telemetry, and that's it. But then the content is not that hard. Yeah, sure, we have multiple formats, but that's like 10, 15, 20, 100. How many possible like formats exist online for something like Google to even tell you similarities in recommendations? Like, it's a lot harder of a problem in computer science for all of these other applications. But we're acting like in cybersecurity we have hit the edge of human knowledge in computer science. Like, come on, like correlation has been solved in the 60s in every single application. Our phones used to have keyboards. We don't have keyboards. You don't need to ever write a correlation rule. You don't know what's a correlation rule on YouTube. It doesn't even allow you to do it. There is a search, and we will just tell you every time you look at one data point, other relevant data points to it. You look at one product, here are other similar products. You look at one account, here are other similar accounts. You look at one post, here is the whole feed of things that are relevant to it. Not in cybersecurity. Why?
Because on YouTube, if I can keep you on your feed by giving you recommendations, some security and cost center.
Mic drop. Humongous mic drop. Yes. What's your name? Adam. So Adam figured it out. He's like, follow the money. YouTube needs to give you good correlation to make money. Because they don't come and they tell you, you're going to pay us per terabyte ingested a day. That's a messed up business model. That's a very crooked business model. Like, it's not tied to value. It's tied to volume. I'm paying by log volume, not log value. While on YouTube, the business model is the value of the correlation. Because the better correlation I give you, the more you're going to watch stuff on my platform, the more you're gonna see ads. So imagine a world where the SIM is not paid by terabytes, it's paid by ads from conferences that appear in your SIM. That SIM is gonna be so freaking good, your face would be glued to your SIM. Like, correlations would be so freaking good. Like, they would want you to love your SIM so much, you wouldn't be able to pull your eyes out of it. You'd be like, dude, look at these stories. Like, this incident happened here, this root cause happened here. Whoa, like, look at this, and look at that, and look at that coordinated attack. It would be beautiful, it would be seamless. And you would never have to have a content library for your detection and your correlation. It would just work because the money would be aligned with that. Today, the money is not aligned with that. Today, the money is aligned with let's crank up the amount of terabytes. So you see your logs are inflated. Your logs have keys and values. Why do I have keys for every single log? What's up with that? Like, what happened to, knowing the header of a CSV, for instance, on an Excel sheet, and just knowing like the key at the first position is always going to be that. There's no need to always give you key and value. Yet in cybersecurity, we have JSON, like we have XML. We always have key and value. If I open any SIM and I look at any log format, key and value to inflate things. We would like to inflate it. Have you looked at logs before? They're highly redundant. They are so redundant. I can show you some. They are ridiculously redundant. Here's a bunch of logs. Look on the right at these logs. From again, a few milliseconds. Repeating IP, repeating ports, repeating everything. So what's the point? Everything is inflated, right? Because Adam said they get paid by log volume, not log value. So you will always have difficulty with correlation, and you will always have extra inflated volume for everything, because always follow the money. So now that we know why, we already are halfway through with figuring out what to do. We already have a problem to fix. And the problem is we have been fed the idea of there is so much data, and we are supposedly in need of correlating some of it. In reality, all of it should be correlated. Every single thing. Like all of the videos on YouTube are correlated. Correlation is not special. Everything should be correlated. There is never a single log that represents an activity. Like me going to this slide right now generated thousands of logs across Windows event logs, across sysmons, across my FortiGate network, UTM, across my web proxy logs. I'm generating so many logs for one little traffic session, right? So everything should be correlated. And content that looks like this does not exist anywhere in the world. This is just creating difficulty. And ideally, you're consistently getting your groupings. And how do groupings look like? How do these correlations ideally look like? Well, they should look like a story. Remember, I told you the narrative of I went to YouTube for a few seconds. That's a narrative. That's a grouping. So in cybersecurity, what are the dimensions of the grouping? The what, right? The what in cybersecurity is usually MITRE ATT&CK. Anybody familiar with MITRE ATT&CK? Yeah? Okay, most of the people are familiar. If you're not familiar, let me elaborate. What is MITRE ATT&CK very quickly? MITRE ATT&CK, my friends, is very simple. It literally just tells you, it's a framework of abstracting events. So if I send you some sort of an event, some sort of an email, some sort of an initial access event, I can just call it an initial access event. That's just an abstraction. What is the point of that abstraction? Is I'm just essentially grouping a few different things and I'm calling them initial access. Why? Because every time there is an initial access kind of event, I can assume that there is causality or sequentiality in the next step. There is always going to be a puzzle piece that plugs into that initial access, and I will assume that that other puzzle piece is going to be called execution, and excuse my AV going crazy here. But regardless, now that I know that there is always a sequentiality, I can essentially group things based on that MITRE ATT&CK. sequentiality there, and I will make stories in cybersecurity attacks that look like here is how the sequentiality went in cybersecurity, essentially attack campaigns or cybersecurity coordinated attacks. So going left to right, there is sequentiality, and going top to bottom, there is timeline, and then with color coding, essentially you know the who. So the who, the what, and the when. The time, the abstraction of what happened, and the when. If I have these, I already have the basic idea of groupings for everything that I will need, and a basic, essentially, format for these groupings. And the grouping logic, as I said, is no more based on these kind of like fragile and kind of like narrow rules or brittle rules. It's just based on the idea of, oh, these things happen to be similar, and we just group them, right? So the analogy here is kind of similar to like if you look at your wardrobe and things are like nicely grouped into like, you know, here are all the black t-shirts, here are all the whatever, here are all the socks. That's essentially the idea of grouping. If you don't really have groupings, you have a hot mess, which is what everybody has today in the sim, a humongous mess of essentially a bunch of shirts and a bunch of pants and a bunch of stuff all over your wardrobe, and you're like, every time you open it, you get overwhelmed, and you're like, where do I even start? Like, where does this go with? And you start an investigation to figure out what goes with this black t-shirt for an outfit, right? Like, so ideally that's not your wardrobe, ideally that's not your queue that you're looking at, and ideally you're able to essentially get a sense of things that are relevant to each other, and essentially instead of looking at one alert at a time or one log at a time, you're looking at stories essentially, and the stories again are going to be these kind of groupings that tell you what happened within thousands and thousands of logs into just a simple narrative. So you go from, again, millions of isolated and siloed things into essentially a few hundred groupings that are essentially stories, not without any content, with the same technology that we've used in the 60s. There's another benefit of that, which is if you insert that essentially before your sim, if you insert that kind of grouping logic before your sim, you can do something that's very, very nice. Once you group, you're able to dedupe. Once you group, you're able to remove the redundancy. Remember the redundancy we talked about in the beginning? The inflated log design that has a lot of redundancy. If you're able to group things before the sim, you're able to drive down the cost, drive down the volume, essentially condense the volume and compact it and compress it so that you're kind of like deflating the extra inflated logs to ensure that you are not just getting better groupings for your IT folks, but you're also getting essentially cash savings, and you can actually reduce that 12 million or 12 terabyte a day into something that's more manageable, closer to like half a terabyte a day, because you're going to be saving a lot more than 50%. The savings are usually like 99% if you just do very basic deduping. And again, any kind of grouping and any kind of deduping. It's not like there's like a very advanced level of grouping that you have to do. Any kind of grouping. So you can think about like basic aggregation. If you did very, very basic aggregation on the same source IP, source port, destination IP, destination port, even that level of very simplistic grouping, you're still able to drive a crazy amount of essentially cost benefits to your sim. Like here are a bunch of, I guess, numbers that you can take a look at. Like, let's assume Splunk for a second. Assuming a very basic condensation, you're looking at essentially reducing something like, let's say, 16 instead of 12 into 1 terabyte. And that immediately creates savings of at least $13 million on an average scenario, or up to $18.5 million. So you can essentially take a lot of that money being wasted on these essentially inflated logs and put them towards actually hiring people. And again, if you're saving 13 million, you're hiring 130 people in theory. So quite the ability to fix a lot of our security issues with just basic grouping and deduping. Not just correlation, but also the ability to save a lot of the money being wasted on these kind of inflated logs. With that in mind, just to tie it off, try to, before the sim again, and this can happen in your data pipeline tools. So whatever data pipeline you're running, if you're running Splunk Forwarder, or if you're running Logstash, or if you're running whatever pipeline software that's feeding into your SIM, that pipeline software is at a nice position where it can run your grouping and your deduping. And essentially, that kind of grouping and deduping will, again, hit both better correlation, better experience on your SIM. Things are grouped naturally, like things are grouped in literally every single app you use. And at the same time, you can see the 100 terabytes becomes 1 terabyte. Not because the grouping, again, is special, it's because the logs are inflated by design. Like we're doing things like key and value, we're doing things like redundancy, we're doing things like essentially a lot of duplicated schemas and a lot of like inflated formats. So really the savings are kind of like a no-brainer in this case. But essentially, if you take a look at methodologically, what are we doing? After the grouping, so after we do our grouping and deduping, we can take some of these groupings and make more advanced groupings. So the grouping logic never stops. It's kind of like making playlists of playlists, right? Or it's kind of like making email threads and then making essentially email labels for the threads. Like it's like advanced levels of groupings. So your groupings can be multi-layer, and essentially some of your grouping logic later on can become more causal to reveal specific attacks, like we were talking about earlier, like how an attack would look like. That could be essentially an advanced level grouping, while more simplistic groupings like very basic aggregation can also still happen, and you can unpack your data in multiple levels of groupings. Any questions so far about the grouping logic? Yes? This is the natural approach. Oh yeah.
There's like a scenario where maybe that additional context at time sensitive investigation second.
I mean,
Lose that when you
no, you like at the end of the day, you're not losing granularity. You're just saying that all of these logs are together, and you don't really have to lose any granularity. It can be completely reversible. Like you can essentially, like here's an example. We don't have to go. We don't have to go theoretical on this one. So there's this article that essentially shows one person essentially goes to a website for a few minutes. Immediately they are generating these 50 net flows and 50 logs and 400 sysmons and 1,000 Windows event logs, and you can see them here. You can download them and take a look at them. And then here, essentially, you get a 93% less volume JSON in elastic comment schema that represents the exact same thing. And here's how it would look like. So you can see I have every single timestamp in strings. Like it's not even, it's not even that, I guess, processed or normalized. Like it's, like you can do the laziest kind of grouping, and it still delivers 93%. So it's the theory, it's the method of the grouping that matters most. The implementation of your grouping can be as good or as bad as you would like it to be, but any kind of implementation, even the worst kind of implementation, would still deliver incredible values both on the quality of your incident analysis, as well as, of course, the alert fatigue and yada, 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 as well as the things that matter to the boss, which is judging, and also matters to you so that your team can actually get 130 more people, like, instead of, putting weird looking logs into your SIM. Any other questions? But yeah, of course, you can implement a million versions of your grouping. Some people might want to lose more data, and some people might want to keep all of the data. Some people want the grouping to be completely reversible. Oh yeah, we have a few GitHubs. So here's one of our GitHubs right here, the attack flow detector. So this kind of GitHub repo would show you essentially an entire open source implementation of this that correlates things and does this grouping very easily, and you can essentially just put it in whatever configuration and whatever data pipeline you want. Can do it with ChatGPT if you're not a coder. If you're a coder, you can like just drop it in into your essentially pipeline, whatever software you're using for pipelines. Yes.
So, this is all great. I wonder, so you still
So this is completely the same thing. We didn't reduce data fidelity. This is completely reversible as well. It,
So you're still storing the mass volume of logs. It's just maybe not in the SIM, so it's cheaper, right?
no, it's still in the same.
The raw logs.
Yeah,
My point is you ingest the same amount of raw logs and you have it saved.
it's just a different representation. So it's a different representation of the same logs. So the same logs are there. You just represent them in a way that's smarter and neater.
Okay, but originally you were talking about ingestion costs, right?
Yeah.
Ingestion costs.
So you can think about this room, and this room can be essentially a bunch of JSONs. Every person has a JSON, and every person can be represented as a JSON today that has a key, attended this session, and then yes. This is a very bad inflation of the format. Instead, you can represent everybody by a CSV entry with no keys, and essentially comma, yes, where it says attended essentially the session. Even better, you can group everybody that attended the session and have one yes instead of 50 yeses. So these are all ways to represent rather than reduce the granularity. And they're all reversible. I can essentially take that CSV and create 50 JSONs and again add the keys and values if I want. It's just different ways to represent. One inflates the size and one condenses the size.
Sounds like the differentiation in what your auditor is going to accept. Because some auditors or some regulatory bodies are going to say you have to have all syslog events for 30 days, and it's a checkbox. So
They don't tell you how do you want to save it. Like they will tell you, I want you to represent everybody in this room and don't lose the data of everybody in this room. But they don't tell you, do it in a JSON, please, and everybody should have a key and value and be very redundant on the same key and the same value 50 times instead of representing the same value and key once.
I understand.
They don't care.
I understand the difference in the representation and the ease of doing the alerts, like the binding.
It's a compression logic. That's how we compress things. That's how you take a terabyte worth of data and you do archive to zip, and somehow it's like 100 gigabytes instead of 1 terabyte. And you can completely reverse it. You can be like extract. It's completely reversible. It's compression. That's exactly
So the volume comes in and it becomes compressed.
Yeah.
Inside. Okay, so
and it's a better representation. It's a compression that looks better for investigators. Investigators don't like the redundancy of the same key, the same value. Like it's more chaos. It's more noise, and that's why more people would raise their hand when you say, "What's the biggest problem today?" Oh, correlation. Yes, investigations are very hard. Like they're not hard. You get fatigued because the data is garbage. The format is garbage. The data is good. The format is inflated, and it does not serve any purpose. It was not made in this representation for you. It was made in this representation for the business to get more money because they charge by volume. Yes.
I think your concern is more about the deduplication, right? Like losing logs.
Completely reversible.
no, so I was just trying to get my head around how the actual reduction in congestion is happening. That's what there is a counterpoint of yes, where some regulatory might need full logs. To your point, most of the frameworks will say you need to be able to do this. They don't necessarily describe exactly how to do it, so you can get away with that. So I have effectively the same what you're asking for is good enough. Whether that holds out, it just depends on what's going on. It's not full PCAP, so it's not perfect either way. So I was just trying to get my head around where is the actual reduction in volume to then lower the SIM costs, right? Because it's all, anybody who's ever stared at a SIM is always like, why are there thousands of these same exact logs that I don't ever want to see, right? So.
I mean, it's just a compression. Like that's how we compress things. It's a completely reversible. Theoretically and ideologically and logically, it's equivalent. It's equivalent stuff. So you didn't lose any data. But yeah, any other questions? If not, I appreciate you. Very, very grateful. I'm happy to take more discussions on the side, so we leave the room for other people. But I appreciate you. Thank you very much.
Hi, everyone. Thank you all for taking the time to attend my talk today. My name is David McDonald. I'm a software engineer at Velexity, where I work on our Volcano memory forensics analysis tools. And today I'm going to be talking to y'all about detecting, deobfuscating, and blocking fileless malware with TreeSitter. So I think the best way to kick things off would be to show y'all Windows AMSI interface in action. For anybody who's not familiar, AMSI is the anti-malware scan interface on Windows, and it's really PowerShell's first line of defense against malicious scripts. So anytime you run something in a PowerShell interpreter, it's going to get handed off to the AMSI provider DLL. In this case, the default is called mpoav.dll, and it has a method called scan buffer that is going to read the contents and determine whether or not it is malicious or clean or unknown. So what you see here is a setup that is typical of a lot of attacks where you invoke REST method, pull down a PowerShell script from a C2 server, and then in the second part, after I demonstrate the actual script contents, you'll see that it is going to be piped into IEX, which is an alias for invoke expression. So for this first sample right here, this is a run-of-the-mill PowerShell-only AMSI bypass that I pulled off of GitHub. It's really popular. It has probably hundreds, if not thousands, of stars, and it does a whole lot of nasty stuff. It's going to create an API for accessing get proc address, load library, virtual protect. It's going to load the actual AMSI provider DLL into memory, patch its DLL get class object function, and then deactivate any initialized AMSI providers. And after that, it will, in theory, be able to do whatever it wants for the remainder of that PowerShell session. So if we pipe this into IEX, we can see that AMSI did its job. It detects malicious script content, and it blocks the script from executing. So over in the event logs here, I have no idea why I can't click on that. You would see event ID 116, which is Windows Defender has identified malicious script content and blocked it. Now let's take a look at another variant of this, which is bypass 2. This is the same script, but with a few tweaks. I took that definition of types that is going to, define get proc address, load library, etc., and I split it into 5 different variables, concatenated it together, and then updated these like shellcode definitions here as well. And let's try running this instead. So AMSI did not detect that, and now if we go to rerun the first script, it just allows that to execute as well. So we can see that AMSI has been disabled for this PowerShell session. So that's not exactly what I would call a high degree of difficulty attack. And the way I was able to do that is by using this tool called amsitrigger.exe and passing it the first script. And I haven't read the source code too closely, but what I'm pretty sure it does is just bisects the script piece by piece until it finds the strings that are going to trigger AMSI. It hands off each chunk of the script to AMSI, says scan this and let me know if it's bad. And then if it's bad, it prints it out. So you know exactly what you need to go modify in your script, and then you can just do it. So AMSI does a great job against that, but struggles mightily against even simple obfuscations like this. They didn't even reorder any of the strings. This is from the actual GitHub repo from November of last year. It says system.management.automation.amsiutils is being flagged now. Just do a basic obfuscation of it like the example, and it works again. And there are several popular open source obfuscation toolkits. invoke obfuscation being most notable among them. Attackers are lazy and they will use these tools if they are known to work. And the reason they work so well is because scanners are just not aware of the actual programming language syntax. They're just scanning unstructured streams of bytes. That makes it extremely effective against anything that is signature-based. Even sophisticated Yara rules can be bypassed pretty easily. And these obfuscation tools have the other side effect of slowing down your analysis, of understanding what might have happened on the machine. Even script block logging sometimes isn't going to show you everything because token and string obfuscations are not deobfuscated within the 4104 script block logs. This is an example of a Yara rule that is attempting to detect obfuscated PowerShell. So you've got 3 strings. One of them is .invoke, which is looking for like invocation of dynamically constructed methods on objects. And you've got 2 other strings that are components of format strings. And the condition here is that it needs to hit at least 10 or 11 of all 3 of these in order to flag. So you can see why a lot of things might slip past something like this if you're obfuscating a smaller script. So you're really just like doing your best against something that you're not really equipped for. And to the naked eye, it looks pretty obvious that this is bad. Like, if you saw this coming through your event logs, you would be like, that is bad. I don't want that running on my system. I have no idea what that is. And that's because we as humans understand programming languages. We, in our minds, can sort of see a syntax tree and know that like a lot of bad stuff is going on. This is another one that I looked at when I first started working on this back in early 2024. And it got me thinking, okay, I want to do 2 different things here. One is design a better way to scan for these things. And another is to, if possible, just unwind these obfuscations altogether. And that's what I was able to do, is design a tool that can, piece by piece, go through the script, rebuild as much of the source code as possible, and provide you with actionable intelligence. This is actually slowed down greatly just for demonstration purposes. I put a call to like sleep in between each iteration. But in reality, this is a very fast process. And the key to this is what I called atomic operations. So what do you really need to do in order to understand that this is a string that you need to glue back together? Well, you need to know that the left side is a string literal, like an actual node in like the programming language syntax tree. And you need to know that it occupies bytes 0 through 4. You need to know that this is an addition operator occupying bytes 5 through 6. And you need to know that this is another string literal occupying bytes 7 through 11. And finally, you need to know that all of these together are forming an additive expression occupying, occupying the range 0 through 11. So if you have programmatic access to all that data, then you could, in theory, just do what you need to do to fix that up and make it a single string. And that's where a tree setter comes into play. A tree setter is a parser generator, originally developed for the Atom text editor and is now fully integrated into NeoVim. So you install your language grammars and you automatically get AST support for whatever language you're working with. The grammars are written in a kind of funky JavaScript dialect, converted to JSON, and then transpiled into C source code for a super fast, lightweight parser that allows you to get updates to the actual syntax tree on every single keystroke as you edit the document. There's strong support for most mainstream languages, and there is an active development community of less common languages even. And my first exposure to this was through queries, because I was watching YouTube one day, and there was a video on how you can get highlighted SQL syntax inside of your embedded strings in another programming language. I do a ton of work with Postgres queries, so I was like, this is something that I really would love to have. You can get instant feedback on whether or not the query you're typing within a string is syntactically valid. If you look down at the bottom there, you can see that although we are in a multi-line Python literal, the text is actually highlighted as syntax because I have told NeoVim through the tree sitter API that I'm looking for anything that matches query should be highlighted as SQL, more or less. So it lets you do all kinds of fun things like your language injections, also advanced code navigation, automated refactorings. There's actually like a really cool ecosystem of tools that has cropped up around this. Here's an example of what a query would look like in Python. I chose Python here because it has a very simple grammar and it's easy to understand. On the right side, you have your actual source code. Note that ID here is not part of the source code. On the left side, you have the syntax tree itself on the bottom left. You can open this by running the inspect tree command in NeoVim. And on the top left, you have a query. So this says I'm looking for an assignment where the left identifier, which I'm going to call ID in a named capture, is equal to foo. And tree sitter within NeoVim says, hey, okay, that's what you're looking for right there. It's a left-hand identifier named foo. Here's another example of looking for a binary operation between two strings, so like hello plus world. On the left side, it's a strict equality check here in this clause. On the right side, it is a regular expression match, so it can be WORL, it can be world, it can be world, whatever you want it to be. And it'll match that and label it as hello world binary. So it was fortuitous that I started looking at this at the same time that I had been exposed to some of this obfuscated PowerShell malware, because I was like, okay, if we can find out grammar for PowerShell, then maybe we can start doing some really cool stuff in terms of detection and maybe deobfuscation. And that's when I saw that Airbus CERT team had resurrected the PowerShell grammar from the Microsoft repo grave. Theirs was pretty abandoned and not functional anymore. So once I got that installed and started playing with it, I was able to start doing things like detections. So this is an example of PowerShell scanning for something that you wouldn't really want to see in your code. This looks for the command invocation operator, followed by a parenthesized pipeline containing a format expression in the middle. You generally would not want to see something like this in your source code. It's kind of a tell. And what I love so much about this example is that you're looking for basically a dot, and then something on the inside that you really can't write a regular expression for easily. I mean, I would say maybe even at all. So what are you going to grep for the letter like period? I don't think that's going to work very well. But when you scan for this with something equipped for it with tree sitter, it sticks out like a sore thumb. So I used a tool called Tree Grepper, integrated the PowerShell grammar into it, and started searching across a repo that I had just like applied obfuscations to, specifically the format string obfuscation to see how much I could come up with. That Yara rule you saw earlier had 86 hits, and Tree Grepper had 616. And not only that, but it pointed out the exact contents of each node within each file syntax tree that contains this. So I was like, that's awesome. That's a really cool and simple detection for something that you wouldn't want to see in PowerShell code. So to get to this, it required a few more steps, well, several more steps, which was figuring out all the different types of obfuscations that I needed to unwind. Now, there are existing methods for deobfuscating PowerShell. This is one of my favorites. It seems funny, but it actually works sometimes, especially on, like, if you just feel comfortable running it in like a Linux sandbox with the PowerShell interpreter, you can do it in there. But The problem with that is, number one, it's kind of a heavyweight solution, and number two, it doesn't really scale well when you have potentially thousands, tens of thousands of endpoints. That's something that we think a lot about at Velexity is how can we make our solutions scalable? There's also revoke obfuscation. This isn't really a deobfuscator as much as it is like a detection engine, but it's written by the same guy that wrote invoke obfuscation, so I assume it works well enough. And then there's tools like PS detect and power decode, which are PowerShell-based tools, but they are for deobfuscation only. It's a heavyweight solution. You have to run it in a sandbox since you're actually using a PowerShell interpreter. It doesn't scale well across large data sets, entire enterprises, and it does not handle corrupt data. So if you pass a PowerShell interpreter something that has even a single character off and it can't form a valid syntax tree, the interpreter is just going to choke, and you're going to be left trying to manually touch up the script. So when you pull things out of memory, for instance, you don't necessarily have that guarantee of integrity. And this is what these tools would kind of do is, my God, stay. It would override the invoke expression command, for instance, and have it just write host whatever the parameters are. So instead of executing the script block, it would just print it to the screen. So you're kind of taking a PowerShell interpreter and trying to patch it back to a point where it doesn't do bad things. So yeah, if we look at the challenges associated with detecting this kind of malicious PowerShell, you've got all kinds of different data sources it can come from. It can come from file collections, it can come from script block logging, C2 endpoints that you might pull it down from, cache files in memory, process memory, kernel memory, free memory, just address spaces, or even network traffic in some rare cases. And again, you want it to be scalable. Ideally, you'd have a solution that is cross-platform and very fast, and something that can process a ton of data very quickly. So invoke obfuscation uses several different types of obfuscations. For instance, you've got your token obfuscations, AST, string, etc. Token obfuscation is really, really easy to detect with TreeSitter. Like injection of ticks within a command name. I need to quit clicking this. So this might actually throw a signature-based scanner off. You know, you're breaking up the characters that it might have as part of its regular expression. But what's cool about TreeSitter is that you can actually look for command names and find ones that contain these things. So instead of being a method of evasion, it becomes a major tell. And this is how easy it is. You can just write this query right here, like look for a command where it matches any characters with a backtick followed by any characters, and it'll highlight it perfectly for you. Here's another example of a token obfuscation, which is the splat concat method of basically breaking things out into different string parts and then executing them. Very easy to detect as well with a TreeSitter query. And then you have AST obfuscation, where you manipulate the ordering of the AST nodes. This doesn't really affect TreeSitter's ability to query substructures because the queries are not sensitive to the ordering of the nodes necessarily. And this is string obfuscation, where the entire command gets like broken down into a string, and ultimately it's going to get invoked with a IEX invoke expression, which is being constructed from the PS home variables here. So again, you've got the command invocation operator. You can look for the command invocation operator with a pipeline of concatenated strings, including variable names. And you can use typecasting also to try to mess with the data types. So you've got a format string, but you're going to build the actual characters by casting integer values up. Super easy to find character casting as well. So what I did was I wrote queries that would find each of these individual operations, and then wrote a callback to perform when each of them is found that would update the syntax tree with the value that I thought was more appropriate. So if it's casting an integer to a character, just replace it with the literal text of the character. If it's two strings concatenated together, just make it one string. And you just basically execute all of these queries in a loop until you can't find any more of them, and then you stop. Another thing that's useful is because you have access to the variable names, one thing that's really common in PowerShell obfuscation is for attackers to give variables really garbage names like B5DAR2. When you have many of these in a script, it increases the cognitive load of you trying to understand it. So you can find all the variable names very easily and just replace them with something like this. This is like this is the same library that like names Docker containers is what I use to generate that. So once you have all these things together, you can do some really advanced unpacking. This is creating a script block from basically a gzipped base64 string. And within the base64 string, it's been cut into pieces, like you can see right here. You've got format strings going on. You've got the call to from base64 string. You've got a gzip stream, and then you've got script block creation. And the cool thing about the queries is that if you design them right, they won't execute the callbacks for from base64 string, from gzip stream until all of the other format strings and concatenations have been worked out. So this is that exact sample being unpacked using the same method, and finally you get okay, can't beat it. There we go. You end up with the actual script that you're trying to find, which contains a base64 string being converted to a byte array, and yeah, much easier to understand. Another huge advantage that TreeSetter has is error recovery. It can handle incomplete or broken scripts. It just replaces wherever it stops parsing valid source code with an error node. So it allows you to actually deobfuscate even if it's not a completely valid script. So this right here is an attempt to run a broken script in PowerShell. You can see that it's going to just choke on the missing terminator. And here is the same script being deobfuscated. Even though it doesn't form a fully valid syntax tree, enough nodes are valid that it can still do work. So I had gotten to the point of that level of deobfuscation, and around the same time, the same team that had resurrected the PowerShell grammar, Airbus Cert, came out with this -1 library end tool. And it is really cool. And I was looking at the source code of it. What surprised me was that they took a completely different approach to things. There was not a single query used in the entire library. And instead, it's based on a depth-first tree traversal combined with a visitor pattern. So you have rules. Well, you have this rule trait, and you have rule mute. Rule is for just visiting the syntax tree and performing an action on each node. You have two opportunities to do something. You do it when you enter on the way down through the traversal and when you leave again on the way up. Rule mute is very similar, except you're allowed to actually mutate the nodes themselves. So you can change the text, delete them, do whatever you want to do. So this is another GitHub page. It's the PowerShell Obfuscation Bible, and I really enjoyed reading this as part of this work because a lot of the things that they call out as like excellent obfuscation techniques are actually extremely easy to detect with TreeSetter. this is an example of low entropy obfuscation where they've assigned these random variable names. Again, that makes it really hard to interpret. But the problem with that is that it skews the entropy of the file and will set off some scanning engines. So you do something like this instead, just create giant variable names full of f's, and now, you've got a low entropy document, technically speaking. So at this point, I was like, okay, we've got a really awesome Rust library, the ability to write rules, and also Windows for Rust has been coming along. So I was like, what if we can give AMSI a boost and merge these two things together? So after much pain and suffering, I was able to get a working AMSI provider written in Rust and load it onto a Windows VM. Let's see. All right, so on the left side here, I'm basically tailing a log file that my own custom AMSI provider is going to write to. And on the right side, I again have a PowerShell session, and it is going to execute some payloads in the exact same manner as before, where you download it via invoke REST method and you pipe it to IEX. So there's our original script. You can see on the left side, it logs my invocation of invoke REST method. You get the hash, you get the total bytes. And you can see that the source of it is from memory. Now, when we run that one, again, the default AMSI provider detects that as malicious, as it should, and it gets logged in my log here. But let's look at that second payload that was the original AMSI bypass. This time it gets flagged, and this is because of the custom AMSI provider DLL that I have installed alongside the systems provider. So if you look at the output here, it's not the nicest log format because this is just a demo, but you can see that it had a string match on system.management.automation.amcutils, and it has dumped the decoded, deobfuscated source code right here. You can see the original declaration of all of the kernel 32 functions. You can see the original shell code. It has even forward substituted the variables into this byte array here and completely deobfuscated system.management.automation.utils. So now we've got an AMSI provider that has a real edge in that it does understand syntax trees and can start detecting things at a more advanced level. So if we look at that low entropy obfuscation again, let's take a look at a sample that tries to do that. So this is a really simple example. I didn't go too crazy with it, but you just define some variable names that are long and have a single character and are, again, not something you would typically want to see running in your PowerShell environment. Something is up with that. And when we run that, why am I not seeing something here? There we go. There was just a delay. You can see that it has flagged variable entropy in 4 different parts of that script. So again, one of the things that they considered a powerful tool of evasion is now making them stick out like a sore thumb. And that's a Shannon entropy calculation below a certain threshold for variables that are of a certain length. That way you don't get like false positives on small little variables. Again, with the quote injection, it says you can obfuscate commandlets by adding single and or double quotes in between their characters, as long as it's not at the beginning. And it's super effective. For example, the expression IEXPWD can be substituted with all of these different variants, all of which might be effective against your traditional scanning engines, but are going to be easily spotted by a syntax-aware scanner. Another cool feature is because you can detect comment nodes within a syntax tree, it renders this entire technique irrelevant as well because you can just bulk delete comments. Comments are another way that entropy values are commonly tampered with. I've seen lots of samples on, for example, Malware Bazaar, where you have a gigantic script that encodes like an encrypted executable, but to affect the entropy of the whole document, they have put in just, tons and tons of comments. So this got me thinking about, well, why let our good YAR rules go to waste? So that Intel teams spend a lot of time and energy developing them. And I think we can actually make them better because now you don't have to wait for these kinds of things to show up in your process memory, in other places in your environment, like after the compromise has already happened. And the reason we can integrate the two is because -1 actually does something really cool as well, which is it assigns an inferred data value to a syntax tree node. So not only can you see that, well, some rules will do that. So not only can you see that a syntax tree node has, a byte array, but you can actually check its contents. And in this case, you can initialize a vec in Rust, check to make sure they're all like below the size, every item in that array is below the size of a unsigned 8-bit integer or a byte. And if that's so, run a YAR rule on it. So here is an example of a very basic encoded portable executable. This is like the simplest YAR rule of all time, but it's really effective in this context because you kind of want to know if there are PE files embedded in your PowerShell scripts. So here we have like a function that is defined that is going to essentially do like an unhexlify operation on this string here and create a byte array of, you can see the 45DA is like an MZ header. So when we try to run that, it gets blocked by my AMSI provider, and the reason is a YARA match right here, and the rule identifier is PE. So we were able to scan with a YARA rule even though we're not looking at raw bytes. And what's really cool about this is that all of these rules kind of are force multipliers. For each one that you add, the whole engine gets better and better. So here's that same thing with invoke obfuscation applied to it. Tons of obfuscations. And when we run invoke expression on that again, once again, it gets blocked. The deobfuscated contents are printed at the bottom here, and we have a YARA hit on that one as well for is PE. And here's, again, another trick that I've seen a lot of is trying to avoid detection of these like hexlified sequences, because some YARA rules will look for those kinds of things by doing like string replacements or reversals. You can actually detect methods written on a string literal in PowerShell, complete the operation, still infer the correct value of the syntax tree node as a byte array, and run your PowerShell or your YARA rules on it. So again, deobfuscated, the script appears down here, and we see our YARA hits. Make sure I'm not overlooking anything here. Oh yeah, this is this R77.ps1 is an example of a payload from the R77 open source rootkit. And I thought this one was fun because it does a very basic, very basic string obfuscation. So character casting, concatenation, does a very good job at scrambling the script contents, but ultimately is going to be deobfuscated very easily. They've got the backticks included in the command names, as you can see. I'm not going to run that one in the actual MC provider because Windows is pretty keyed in on the open source rootkit and is just going to like pitch a fit. But this is the deobfuscated script content, so you can see that it's very effective against those types of obfuscations. All right, and that's what I've got for today. Thank you all for your attention. Does anybody have any questions? If you're not trying to install the actual AMC provider, I think it could still be effective if you couple it with like, you know, just scanning of source code files, for instance. You could definitely write a disk scanner that looks for PS1 extensions and then does all the same steps. Hey.
So when you're writing the .dll to write to IEX to like read the PowerShell script, what if there's a false positive? Like for instance, even though some code might be obfuscated, sorry, English is hard. What if you're like writing it or reading it from a CTF, and for instance, within a CTF, they obfuscated in such a way to hide the flag? What would allow you to be able to dissuade a false positive?
I guess you'd have to question whether or not that is a false positive because it's like obfuscated script. And you would still get the output in the actual log if that's what you wanted to see. So I think in that sense, like you would get your flag, you know? Like, I guess if you really want the script to execute on the system, then yeah, you'll be blocked. But you could also integrate something like a hash-based whitelist or something if you wanted to be like, no, I really want that to run. Go like update a hash-based whitelist in the registry or something somewhere that the provider will read every single cycle and check to see if it can like just let that through. A long time. Just some parts were more painful than others. The writing the Rust provider in particular, the Windows Rust documentation is like not great, and it was really made possible through like one extremely lucky comment on Stack Overflow, where some guy was like, no, I know exactly how to implement like a COM provider in Rust, and these are the exact steps you need to take, and this is how you do it. And then I was like, oh my God, this is exactly what I've been looking for. Somebody buy this guy a coffee and like post this on the Windows Rust page. No problem. Yes. I'm sorry? Could you feed it that? Absolutely, you know? What's the best way to get started was the question? It's a good question. I don't know exactly. I work more on like the tooling side of things, so like real world deployments are outside the scope of what I do day to day. But if I had to guess, an effective way to do it would be to just write a pretty strict set of rules, and like you could do like logging only and just use this as a way to like report things that are coming through PowerShell. Or you could have it consume events from 4104 and parse those out as well. Not really. It's written in C, so it's like, well, the underlying tree setter part is parser is written in C, and the top layer is like Rust, so it's all going to be extremely fast. I'm sure if we benchmarked it right now, you could process scripts like many times per second. Actually, we can try. Let's see. So this is Hyperfine. It's like a profiling tool for the command line. So on average, it runs in about a tenth of a second for a single script. So I think you can put a lot of data through there. Any other questions? Yes. Yeah, like if you wanted it to like post-process events, I'm sure that could be worked in somehow. Yeah. It wouldn't be through the AMC provider DLL. You would probably use this library to write another tool, but it could definitely be done. Anybody else? Yes.
Some of the like when you were developing some of the like trickier obfuscation techniques that sit there and how am I going to
That's a good question. So, and it brings up an important point, which is that this is not necessarily like feature complete yet, because it's working in the opposite direction of like the PSD code tools, which are really essentially winding up with is like a very limited interpreter. So some of the trickier things that I've seen are, let's look at that like PE sample again.
I think it's so crafty.
Oh yeah, they do. Like it's very difficult to catch everything. This right here, like this is something that I had to add, but it basically looks for like a function definition with a single statement that, you know, takes the parameter and does this exact operation. But it, again, is nice because instead of like being strictly matching on the text of this function body, it's matching on the nodes. So you can insert white space, you can like rearrange this function lexically and have it still process this as like a, you know, a dehexified string of bytes. So, for instance, like if this was, if they had applied obfuscations to like these strings, you would actually still be able to execute this rule because all of those would run first, rebuild the original strings, and then this function definition would still match the thing we're looking for. So, and this is something that is like likely to be reused in attacker scripts. Does that make sense? Anybody else? All right, thank you all for your time.
I don't think I need a microphone. Should I do a microphone or no? Probably. Is this being zoomed?
Yes.
How many people are out there? Where's the camera? Hello, Mom. Does this make me a streamer now?
Yes, but there's like a 5-minute delay between live and.
In case I say something really messed up, you guys can cut me off.
Someone else can.
Let me tell you guys how I feel about international conflict.
Guns.
Yeah. It's actually a political talk. Yeah. I feel like I shouldn't be given a microphone. The last time I held a microphone was like karaoke night. Yeah, it was a late night. I feel like this is too loud, but is this good? It's a good time? Okay. Temperature, volume, same thing. All right, hey, good morning, almost afternoon. Thanks for coming in for this talk. I understand it is prime 11:30 a.m. lunch hour, so thank you for enjoying this nourishment of my talk on security research with the Chrome DevTools protocol. I'm going to go jump right into it, do a little storytelling, and then walk through a couple of different interactive code samples and things like that. So if you do have your laptop, you might want to have it open, but it's not really necessary. I'm going to basically switch between slides and a little bit of code and a little bit of running stuff, and then you won't miss anything. I've got a GitHub repository at the end and a couple of other links to dig into and look at things. So with that, let's get started. First, I want to call back to an event that happened in June of this year. There's an article out there. Some cyber researchers responded to a report of unusual online behavior from an enterprise executive. So in this case, we're going to go to track through just like the security researcher in this example to try to understand what happened and what the impacts are for this organization, but also across the internet. In this instance, this executive, they are looking at his web traffic and they're like, okay, cool, what's going on? They see that our target, this exec, loads up this URL. And believe it or not, this is a benign URL. This is a real online Saudi Arabian website, and there's obviously WordPress, and there's some cached content here. No big deal. I look at this, I'm like, yeah, this is just more bundled JavaScript junk. But as you might expect, within this bundle is a reference to jQuery migrate 341, so another JavaScript dependency. And then within that bundle, there is just one line of obfuscated code appended to the end of it. All right, well, now we're interested, right? We're visiting this benign site. We trust this. What's going on? When we look at the evidence from this scenario, we say, okay, network traffic looks legit. I see a legit URL that I trust. I'm not worried about it. The file name itself, I'm like, cool, I'm not going to lose my mind over some jQuery plugin. This is some compatibility file. That's fine. And it's not going to throw up any issues in our code analysis tools. Right? If I do an npm install for a jQuery migrate, if it's coming from a legit source, cool, I'm not worried about it. If I've got my supply chain detection set up to look for this tool, I'm like, okay, cool, this is here, blah, blah, blah. It matches our static analysis. Maybe it doesn't, and that's how we see it when that hash doesn't match from the file content. But the point is, in this example attack, the one thing we see is that at runtime, we go to this page, there's actually a fake payment form being injected and exfiltrating data from the checkout page on this shopping website. Let's dig into it. In this real-world supply chain attack, the attack vector is that the user is visiting a legit but compromised business website. So I want to point out, in that example, this is a now compromised platform. We know that, and we want to dig deeper into that. We know we've got this disguised payload, and then we also, I can tell you a little bit more, and there's a link to this article in these slides at the end of it. But the attack further is pretty tricky because in that payload, the way that it runs is depending on the environment. of the target. So like in this case, the payload's loaded up in the exec's computer, and like depending on the rules of the adversary, it might go, okay, cool, I'm in my target's box. I'm going to drop the real payload now, because obviously security researchers like us, we're going to go in and load it up. These adversaries do not just want to drop their payload on all of our machines for us to research and then write a crappy blog post about. Like they kind of want to save that for their target. And that's what makes this really interesting, because security research in the web space is not always going to be consistent. And I just want to mention that to think about as I walk through some of the examples here. This pretty much summarizes everything I just said, but the three main points: static analysis can be difficult, network traffic can be deceptive, and the evidence is often circumstantial. And this one example I point out is just one of many and many. I had trouble choosing what I was going to use as my little introductory case. But whether it's the most recent, I don't know if you heard about the NPM supply chain attack a week or two ago. Somebody fishes for some credentials and just sticks a little obfuscated JavaScript at the end of some trusted packages. If that attack wasn't detected, I don't know, a little sidebar here. In this attack, what I think is hilarious is that this person went to all the effort to compromise some pretty high-profile packages that exist in a lot of dependency chains just to put in like a crypto wallet drainer at the end of it. They made $0. They checked the account. No money came out of it, even though this is easily one of the most widespread NPM supply chain attacks that has happened. But the reason it works is because as long as you've got code in that package, people are trusting NPM. People are trusting their supply chain and going, cool, NPM install. It's not going to show up on NPM audit because they didn't know it was vulnerable until they did, and then they pull these packages down. So it's wild to me how much we are blindly just okay with bringing in dependencies. But as security researchers, it's awesome because we get a lot of cool things to dig into and try to understand about what's going on in the greater internet. So with everything being said there, I've talked about a few examples, things we can dig into. The solution for us as researchers is to just ask the browser what's going on. When we want to think about the evidence that we saw and ways that it might not be so reliable, I like to cut to the chase. Let's load up this sample, or let's load up this page, or load up this JavaScript bundle, and let's interrogate the browser and say, hey, what's going on? What's being loaded? What's the behavior? And then use that to further our analysis of the scenario, and again, discover things just like this on the internet at large. A quick aside, why I feel I'm remotely qualified to tell you about this. I work as a security researcher at a company called BitSite. We're one of the better cyber ratings companies out there. Think of it as like a credit score for your company's cybersecurity. And while that's pretty cool, the cooler thing is we run one of the largest internet scanning pieces of infrastructure out there today, and that is called Groma. Google it, BitSite Groma. There's a couple of blog posts. These folks at Grainoise did some analysis of different benign internet sensors. I'm honored to say we are considered benign. I think it's exciting. But you can also check out some of our CVE discovery data at Groma.io. This is not a sales pitch. I'm just pointing this out because what this data we have enables is a talk like this, where we'll start with one isolated incident, but then think about it on the scale of the internet. And that is the coolest thing, because built into our internet scanning platform is our Groma headless browser. So in addition to fingerprinting services, platforms, kind of like what Shodan does, we'll also go beyond and load up target pages by the million and capture everything going on in that page using things like the Chrome DevTools protocol. So what is it, right? I keep referring to this Chrome DevTools protocol. You've probably heard of protocol and Chrome DevTools, but this intersection is going to be pretty interesting, whether you've got in-depth technical experience or still new to basic Python programming or even basic web development. In a very simplified kind of 100-yard view of it, the Chrome DevTools protocol is just an API to interact with the web browser. Obviously, you can fire it up, hit F11, and start clicking around and digging with things, and that's fine for a one-off thing. But if you want to automate this kind of analysis or dig in and grab every statement, every line, or some crazy complex JSON that represents the DOM tree, the Chrome DevTools protocol is awesome for that. And if you've used automation tools like Playwright or Puppeteer, those are also built extensions of the Chrome DevTools protocol. So if you've used those, you've used the Chrome DevTools protocol. But we're going to go and just focus on the DevTools protocol because there's some really neat internal functions to the Chrome engine that we can use to do what I mentioned before, which is ask the browser questions about what's going on in the browser environment. So if that sounds good, do you folks have any questions about where I'm at this point? I'll have a little bit of time at the end too to take some questions. So let me just get my notes together here and I'll go on to the next section. Cool. Folks who are just coming in, you have not missed anything particularly important. I've just been rambling for about 10 minutes, so we'll keep it moving. So the way the Chrome DevTools protocol works is it's got these domains. Think of the domain as the kinds of questions you can ask the browser about what's going on. This is 5 of some 20 or 30 domains in the Chrome DevTools protocol, but when you think about that analogy of the actual user interface in the browser when you hit that F11 key, these are some of those tabs you'll see. Runtime represents pretty much, the console. The debugger represents that awesome debugging features within there. Network is the network tab. The DOM section is kind of similar to what you get when you do inspect element, and then you can traverse the DOM tree and ask questions about that. And then finally, the page is mostly functional for us when using the DevTools protocol. We'll bring up a browser session and then tell it where we want to go and what we want it to do. The way that the Chrome DevTools protocol works, again, super approachable, and what makes it really fun is once you set up that WebSocket connection between your headless browser and your Python script, you just ask questions through these commands and then get answers through events. I want to point out that in the command section, there's an ID for each command that you provide. That's so you can map that response back through the event. And sometimes the browser will be more verbose and give you additional events you didn't ask for, depending on what domain you enabled. So all those features I talked about before, when we're actually programming this and creating our research tools, you need to make sure to enable those different domains. So to kind of share this with you guys and sort of dive a little deeper, I put together a very simple demo environment. This is our secure shop. Very exciting. You'll notice I bring in that same jQuery migrate dependency, totally unmodified, right? Wink. And then also a JavaScript bundle that's included on the page that brings in some web request tools, Axios, what that called, and then some of the JavaScript to make the page interactive. So let me bring that up really quick. So yeah, here's our little secure shop. Very exciting. I can put in no info and it processes. But this gives you a sense of what a real page might look like with some interactivity and some things going on here. And like we called out before, if I go in and I start making requests, you can see here that there's some interesting stuff going on. We see that it looks like we're hijacking form submission, exfiltrating data. I see an HTTP request to an attacker-controlled domain. Okay, it's obviously something's going on here. Let's use the Chrome DevTools protocol to ask the browser what's happening. So the first thing we'll do is look at observing the anomalous behavior, right? We see what's going on in the console. Let's make sure we've got some concrete evidence that something's funny is happening here and try to isolate what's going on and even where it's happening. The first way we're going to do that is get this irrefutable proof that the browser environment has been altered and that sensitive data is being exfiltrated. We saw some console logs, but okay, I need a little bit more than that. What we're going to do is use the runtime evaluate Chrome DevTools protocol command. This is the best one because this lets you go in and evaluate any JavaScript within the page's environment. So simple as this, I say, okay, hey, I want to go and say, give me the stringified version of the built-in fetch function. Now, I skipped over some details here, but the reason I'm choosing to look at the fetch function is because, like we saw, we made a request on the page, and we see some other things going on there. So we're going to analyze this. I'll explain more once I get to the actual code demonstration too. From there, we're going to say, hey, tell me what the stringified version is of this built-in function. And then we're going to also say, listen for network events that occur after I ask for some information about this method. This is important too because, like I mentioned, if we think something's happening with the web request, we want to see what that data is fully transparently and then analyze that output. So let me go to our first demo here. So what I'm going to show you now, and forgive me, I know I hate to be the guy that gets on the demo and just starts showing you a bunch of little code, but trust me, it'll be helpful too when you go back to this at the end because you're so excited to look at the repository I put out. This common.py, what this is a quick wrapper that I wrote around the Chrome DevTools protocol. So all this is doing is launching Google Chrome for my environment, gives us some helper functions to just say, hey, I just want to do this, or I want to do that, or a little bit of message handling. Like I mentioned before, the Chrome DevTools protocol is just going to continue to give us stuff over the socket, and also give us an easy way to ask for those commands. So you might recognize this format. I need to give it a command ID, that method, so domain.debugger, or evaluate some JavaScript, or whatever else. And that can also provide some additional parameters. Yeah, that's pretty much it. This is used to launch the browser. So just to give you some context, so you don't think, wow, it's 10 lines of code to do Chrome DevTools protocol research. A little bit more to it, and just want to give that context. So in our first example, this phase one of our analysis, like I mentioned, we want to confirm that something's going on there and see if we can get some more information about it. So we enable some domains. We say, yeah, give me page, runtime, and network. We'll navigate to the page, wait for it to load, and then we're going to make our first check. I talked a little bit about this in the description of this talk, but the concept of monkey patching is pretty straightforward. The browser comes with a number of built-in functions, right? You can go in and say, hey, I want to fetch this, or console log this, or error out on this. Those are native, built into the Chrome's V8 runtime environment. But the beauty or curse of JavaScript, depending on how you look at it, is that you can go in and overwrite these behaviors pretty easily, especially as a talented security researcher like ourselves. And the way that is often used is test instrumentation, if you've got some big complex JavaScript project, or if you need to introduce some custom behavior into the tools and platforms that you're using. There's legitimate reasons to do this. Adversaries love to do it too, because they can just grab something off the shelf, wrap it, make sure the fetch still works so no one thinks anything, and then also add a little exfiltration or do some other malicious behavior within the environment. So keeping that in mind, what's really neat about the Chrome environment is that if we're asking for actual stringified versions of these built-in features, in this case, I'm using fetch, you can ask for, hey, give me the string version of this, and if it's native code, that function output will say native code, because that's what it is. It's native Chrome-based C++ code. And so if we ask for the stringified version of this, what we're going to get back is something that'll tell us whether or not fetch has been tampered with. I know it seems kind of like I'm just sort of understanding the problem right from the get-go, but again, we selected fetch because of the behavior we saw on the page. If you were doing this at scale, something to think about is you could just take every every built-in function of Chrome and just ask the page, hey, has this been modified? Hey, has this been modified? Hey, has this been modified? And then you have an understanding of, oh, okay, something weird is going on. Is it on purpose? Is it not? You can look at it from there. The next piece that we're going to do is once we understand that fetch has been compromised, we will also then use this script to understand where the information on the page is going. You saw there was a form there, and then once we hit submit, we should see our form data go out to our destination. Well, in this case, we'll inject a tracking marker. It's literally just a string, just a number that I'm aware of and control. And we're going to ask the browser, hey, where is this string going? Where are you seeing it? What is happening? And what can we do with that? And so less digging through code. A lot of this is just boilerplate I wrote around it to make the demo go smoother. So let me bring up the code here and go from there. So this is cool. We're launching a headless Chrome browser in the background. It comes up, loads the page. Great. Now we've run that analysis that I just pointed out. The first thing is that we can tell it's been monkey patched. When I ask for the function signature, I don't see the fetch code. I see function, fetch has been hijacked, and then there's some more attacker code built in there. Great. Now we know that it does not contain native code, and we know something weird is going on. Next, we'll inject the value that I control, this is not a real credit card number, obviously. You can go try it out if you'd like. We find the form on the page, put the value into the form, submit it, and then listen in on the network domain to say, okay, cool. Do I see the value I'm looking for? In this case, we do, and we actually see it go as a post request to the attacker controlled domain. Great. We know the problem. We know that something's there. We know what it's doing. Let's keep going. This is the same set of slides. I put this in here so when you download my slides later and you're super excited to read about it again, you understand what I was showing you. Now, part two, let's actually find where this modification is happening, right? I've said it about 16 times. We see something's there. We see it's doing something. Let's go a step further. Actually, let me get back here. So we saw fetch was tampered with. Now, this is probably my favorite feature of the Chrome DevTools protocol. And like, again, there's so much you can do with this. In this case, we're going to use runtime evaluate again, and we're going to say, hey, Chrome DevTools protocol, can you just evaluate window.fetch for me? Basically run it without any input. Sure, we can do that. But I'm also going to ask the DevTools protocol, hey, don't give me the value. Actually, when I say return by value false, this is going to return an object ID. It's going to say to the browser, hey, how do you know what this function is? Like, what is it in your memory? Cool, this is the handle to that function. And then immediately after, I'm going to say to the browser, awesome, well, now I've got to handle the function the way you know what it is. I'm going to ask you for the properties and say runtime get properties with the function ID. And of the many things you can do with this, the one we're going to focus on is this internal metadata that the browser has called the function location. And that function location will be the exact source file that this function originated from. And then it's also its location within the file. You can imagine this is great because you can go to a page and say, okay, cool, it says they've got jQuery right here and it must come from this file. Well, let's ask the browser, where did it get this jQuery from? And you'd be surprised how many times you think you're using this version or this dependency, but really it's coming in from some third-party script you don't control. Maybe it's an ad services platform you injected on the page, one of those annoying, dumb chatbots that brings its own jQuery on there. As long as you've got the content security policy configured that you can access all of those resources within your page because you trust them, you don't always fully have the control you think you do about what is happening in that browser environment. So I'll go to the demo now and show off this next piece. It's probably my favorite part. Pretty short here. Again, we're going to enable the same domains, navigate to the page. Then we're going to collect all of these script parsed events. So I didn't really allude to this well in the slides, but another awesome feature is we can load up the debugger and say, hey, forget just parsing all of the network information that comes in when you load the page. Instead, I want to keep track of every script that the browser parses when I load the page. So this tells me not just brought in as a resource, but I want to make sure that Chrome saw this and took note of functions and where they go and what's going on here. And this is really neat because you'll see a lot of things being loaded, not just network-based, but actual scripts that are calling in other scripts either from within the environment or outside of the environment, and then gives us something to ask questions about. And that's what I want to focus on. Again, thinking about the context of this talk, the security research is all about asking questions. And it's a lot easier to ask the browser a bunch of questions than it is to ask the developer if you can't get in touch with them. So we'll load up the scripts in the page. We're going to create a map of those script IDs that I talked about to the resources. And then we'll go a step further and we'll say, hey, window.fetch, where you at? Give me my object ID, and then use those script IDs we just mapped to say, okay, cool, this is where that object is. This is the location. So let me go ahead and run this next bit here. I guess I can make this bigger. So just like we expected, we actually see some of Chrome's own internal scripts being loaded. You know, when you go to any page, there's little interactive bits in Chrome and Chromium and other Chrome-based browsers. But the most interesting part is our dependencies being loaded here. So you see we load up jQuery from the jQuery CDN, and then we've got some of our local scripts that we've been digging into. Most interestingly, the old jQuery migrate, we think. So window.fetch, we grab that reference, we ask for the ID, and we're able to use the DevTools protocol to say, hey, yep, window.fetch did not come from the browser environment. It came from jQuery migrate. That's really weird. But even more interesting, I can go in and say, okay, cool, where's this happening? Let me go to line 4, column 23 of the file, and actually see what's going on. Now, in this example, it's pretty contrived because, as you can see, I just put it there at the bottom, totally in plain text, but imagine this is seriously obfuscated, right? You don't even see the word fetch in there. You're not just going to control F through the source code to find this. Yeah, you could deobfuscate and do all that, but now you've sunk 30 minutes into the problem. And if you're doing this at scale like we are at BitSite, you don't have time to sit down and look at every page and debug the behavior one-on-one or one by one. We want to debug that behavior automatically at scale and generate information about what's going on the pages that we're visiting. So moving right along, discovered where it came from. Awesome. We don't trust that file. Now for the third phase of this is a very short piece of the demo, but just wanted to expose another really cool thing that you can think about when considering real adversary behavior out in the Wild West of JavaScript compromised dependencies. And in this case, let's pretend that our attacker has some kind of C2, right? In the initial example I gave, we are saying, hey, the adversary is actually going to reach out to its malware as a service and bring in the right payload depending on environment context. A lot of the ways adversaries are doing that now is forget doing it in traditional HTTP requests. Let's open up a WebSocket and hide the traffic there so that the more beginner researchers, not us in the room, of course, don't even think to look at the WebSocket traffic and what payloads are being brought in there. So in the same way that we've used the debugger network domains to ask the browser, hey, tell me what's going on when things are loaded, we can also ask it to look at what WebSockets are created and what the individual frames that are being sent and received are. Pretty similar to that first phase, just in a different context. So I will go back and show you that as well. It's pretty much what you expect. Navigate to the page. We've got the network domain enabled. We'll say, hey, let me know what WebSockets are created, let me know what's sent, and then let's intercept anything that comes through. In this example, I gotta be honest with you, I did not take the time to run a WebSocket server, so we'll just see the actual request go out to create the WebSocket, and even then, that's enough. You can imagine that maybe the WebSocket server that the adversary is running is offline right now, right? We don't even want the researcher to think that things are up and running. Launch headless Chrome. Load in these events, say, okay, cool, yeah, I see a WebSocket connection. And you get a connection ID, which, guess what? You can ask questions about that to the browser. It gives you something to trace down and understand what's going on. Here we see, okay, yeah, no activity detected, as expected, whatever. But what's neat too is you might have noticed as well that this reference here isn't even in the jQuery migrate. Here we're exfiltrating using the built-in Axios instance, but in this case we don't even see where that C2 is happening. And that's because I actually bundled that behavior into the app.js. And you can see this is a messy JavaScript bundle, and I believe this one also gets obfuscated. But through the same line of reasoning that I just showed you in the first two phases, we can go find these kind of arbitrary events the same way, asking questions to the environment based on object IDs. So yeah, let's focus back on the scaling problem. You've seen something that you can sit down and do as a researcher. Those phases are just a couple of really simple tools I built, but it's just based on the Chrome DevTools protocol. Once you understand that ask and receive relationship, there's so much you can do. And I want to think a little bit, just kind of ideate with you here about going beyond these isolated incidents and doing research into this. Forget just looking and saying, okay, cool, this is what happened on my server, now I know what's going on. I'd like you to consider this. Let's say we use the Chrome DevTools protocol to visit 100 pages. We know what we're looking for. We know we want to see certain behaviors for window.fetch. We know we want to see certain behaviors for console.log. What if we capture the expected behaviors, create a signature of that, and then visit every single page using these tools and just grab everything we can about what's going on and compare those signatures? Does two things. One, helps us threat hunt much more quickly. If we've got a sample of something a bad guy's doing, we can look for that bad guy behavior across the internet in different packages, in different payloads, and surface those a lot more quickly than you might otherwise by hand. The other thing is we can use that to actually understand better what the supply chain looks like across the internet. A lot of times, if you're an organization, you don't want these automated internet scanners going looking for your jQuery 1.11, right, all these CVEs in it. Folks will sometimes just take the jQuery version string and just remove it. No version. Cool, that fools like half of the simple scanners out there. They don't see a version, they're like, oh, I don't know what this is, next, and they don't even think to assign CVEs to that because the hash won't match, the version won't match. How do you know what it is? Well, yeah, you could do syntax tree matching, right, where you generate a tree of all the behaviors you expect to see and then generate a tree of what you see on the target page. But again, complexity and time, those are both going to be increased with this behavior versus taking advantage of the Chrome DevTools protocol. If I'm already going to the length of loading up the page in a headless browser, this is all happening in the background already. So I can grab that information and keep moving on. Especially like that script parsed event I showed you, really interesting stuff you can dig into there. Another thing that I think is interesting beyond like supply chain, it's really interesting because we can ask those specific questions about what's going on. And when I think about the most recent NPM compromise, you can ask questions of what's like the blast radius of a compromise. Let's say that package didn't go detected. Cool, we can go further and actually try to understand that with our internet scanning platforms. Obviously, I'm gonna guess not everybody in the room has the time, effort, interest, or resources to scan the whole internet at scale, but some of you might be thinking about your own internal tools, websites, your blog site, whatever. An easy way to apply this is just write your own scanning tool for your own environment. Generate signatures of what you expect to see. If you know that checkout page JavaScript is supposed to call in these dependencies and make these requests, and you see it doing something different, that's basic anomaly detection grown by yourself. Congratulations. So that's pretty much the final takeaway here. The browser sees everything, and with the Chrome DevTools protocol, so can you. Definitely check out some of the other domains here. The documentation is pretty well done, and there's a lot of cool demos out there. I'm gonna pull up my notes really quick to make sure there wasn't anything really important I wanted to say. But with that, the final thing I have for you is, one, you can go to my github.com/timtheguy. The most recent repo there is those demos that I just showed you. So if you're interested in that, cool. Yes, I committed it this morning. Sometimes I do things last minute. But if you're up for a challenge, I've also got a couple of small prizes throughout the rest of the day. If you're like me and you cannot commit time to a full CTF, but you want to be able to say you won something, I've got this little mock scenario set up, and if you go to timtheguy.github.io, you'll see I've got this little analytics feed tool, pretty interesting. And if we go inspect what's going on here, say, okay, a payload is being attached to our log entries. Check it out. Fire up some of the samples I wrote for the DevTools protocol. There is a payload that is generated in memory. The payload is just a flag. But you won't be able to control F through the source for this. It's super obfuscated by me. And you won't be able to find that string the normal way. And if you do just want to run this through some deobfuscation tools, go crazy. But the first 3 people to send me a message on Discord, it's Tim the Guy. I've got a couple of ESP32 little mini boards with a built-in display that are pretty fun to tinker with, and I've got a bunch of stickers to give out too. So I'll be around all day. Send me a note if you want to try the challenge. Otherwise, I will leave this page up. That repo has the code. The bottom one is the little challenge, and I will put the slides in that repo too as well, because I realized I lied about sharing them. They're not out there yet. But I think I just blew through this in a good 30 minutes. So it's 15 minutes to ask me questions or go get lunch. Otherwise, thank you guys for being a captive audience. I really appreciate it. My first B-Sides talk, so if you also want to get on Discord and give me some real harsh negative feedback, I would love that too, or positive feedback. But yeah, thanks guys for being fun. I really appreciate it.
Another suit wearer. Let's go. I thought I was the only one. There you go. And another suit. Let's go. I'm Rippy. Eddie, nice to meet you. New York? Nice to meet you. I will. I know, I didn't shave today, and they had headshots too. I'm like, I got it this morning, like, gotta put on a suit, I didn't shave in time. Thank you. This morning I got up not expecting to wear a blazer, and I looked up what should I wear for this? It's like, oh, it says business casual to like fancy.
I feel like a cheap ThinkPad on eBay.
I don't want to think that.
This talk was interesting.
Hay que hacer que tú cuando vayas a hacer cosas te hagan dudas.
Let me ask the people. I have to go.
You get that VIP treatment.
Hello? Okay.
You're good.
So good morning, everyone. Huge shout out to B-Sides and welcome to B-Sides. And thank you to the folks who organized this event. And welcome to my talk. It's based on the anatomical evolution of account takeover attacks. It's primarily a quick insight into the talk. It focuses on how MFA might be giving organizations and individuals a false sense of security. More importantly, on what you can do about it and how attackers have fundamentally changed their playbooks over time and how we have not. So a little bit about me. I'm a security engineer at Together.ai. My name is Shashin Bandorkar, by the way. You can find me on LinkedIn and you can find me on my blog. It's called as Healthy Bite. So just a little bit of trivia for the folks here. Out of curiosity, I would love to learn how many of you, by a show of hands, think that MFA across organizations solves a lot of the issues when it comes to account takeovers? Okay, awesome. 2 people. So for those of you who've raised your hands, you're not wrong. So MFA is a very critical control. And for those of you who haven't raised your hands, I'm sorry, but vendors say you're lying. But here's the thing. So attackers have been studying MFA over time, and it's just become as hard to implement it. And let me show you this thing by a simple analogy. So the analogy focuses on a magician's trick. So we take a street magician, an amateur magician. He starts the trick with a simple deck of cards, and he asks the audience to pick any card. It's a misdirection, of course, but eventually the trick gets stale. You see the slide of deck, you see the hand, and eventually you're able to crack the magician's trick. In this case, an account takeover works simply the same way. For example, over time, account takeovers have been working with something like password spraying, password 123, or some level of credential stuffing, or some sketchy email. But with the magician's trick, over time, the magician learns that, hey, my trick is getting stale, and how do I evolve this trick? And that's where the magician's trick evolves. And the magician adds a layer of complexity to each trick, and turning the trick from a simple trick to an illusion now. And in this case, the reality of the trick is, in a point in time, it takes multiple sets of eyes and multiple perspectives for you or the humans to catch the trick. The attackers are not triggering any alarms, and they go undetected for a long time if you have a singular point of view. And that's how modern account takeovers also work. They don't break down doors anymore. They just steal keys. They learn different human habits, and they walk in like they belong. They're not hackers anymore. They're just method actors trying to play the role of a legitimate user. So let's look at some account takeovers and the evolution of what an account takeover looks like. And I'm going to show you how a progression timeline looks from an account takeover perspective. In this case, keep in mind that these are 3 verticals, and this is the evolution of what account takeovers look like. But these 3 verticals are coordinated campaigns. They work simultaneously. They can work individually as well, but they normally work simultaneously. So the first vertical is based on social engineering. Social engineering, we have gone all the way from Nigerian princes sending emails to AI-powered deepfakes. The progression has been from basic phishing with typos to spear phishing campaigns to real-time phishing proxies. And you will see this proxies like Evil Engine X that steal the MFA. And now it's gone into AI-powered deepfakes, impersonating your leadership like CEOs, CFOs, etc. And with the rise of AI, you may have seen attackers use AI to clone these voices of your leadership. Vertical 2 focuses on credential stuffing. So credential stuffing has gone from evolution from basic brute forcing to surgical precision. And the progression has been from password lists from breaches to automated bot attack at scale. And eventually they've got smarter and they've become slow and distributed in their attack lifecycle. And these attacks have gone under the fly due to rate limits, etc. And now they're buying different combo lists on the dark web or in a breach that a company might have had, and they're buying combo lists in this way, like passwords with security questions, with recovery emails. And one breach for any company becomes their skeleton key to your entire digital life. And the third is a more newer take. It's not been newer right now, but it's been there for a while, but supply chain attacks. So the scariest evolution of supply chain attacks is it starts with compromising small vendors. So something like a small application or a Chrome browser application in this case. And they've moved to trusted OAuth applications where they're abusing different trust relations, and they're requesting permissions on your behalf. And these permissions might go under the radar. And eventually, once they have permission creeping, they're infiltrating your marketplace. So for example, an app like Zoom has multiple different third-party applications, and you don't really know who you can trust in there. And one app, you compromise one app and you're pretty much compromising the entire marketplace, and then you'll actually move into different applications in your life cycle. And the big issue here is, like I mentioned, these work simultaneously. They're in a coordinated campaign. So I'm going to walk you through what an account takeover workflow, a compromised workflow looks like, and this is straight out of an attacker's playbook. So any account takeover starts with identifying the target. So once you've identified the target, you gain primary credentials, which can be gained, let's say, user email and a password. And this can be gained from data breaches or social media, just simple guessing. But the next stage is where we want to make sure that do you have MFA, and that's where the critical control comes in. And let's say in this case you have MFA. So if you don't have MFA, the attacker gains simple bypass, and we can directly access your account. But let's say there's MFA involved, and now the attacker has to bypass MFA. And that's where the account takeover compromise happens. So in this case, when there's a bypass, there are multiple different paths that an attacker can take. And these are different attack vectors for the attacker. The first one is MFA fatigue. So your MFA fatigue is basically continuous spam push notifications until finally someone checks out and says yes out of frustration. The prime time here is based on human psyche, and the success rate completely depends on the user. Once the user workflow approval goes through, and unauthorized access is granted, and basically the account is compromised. So let's say if the user doesn't approve this workflow, even though the attack fails initially, this is a temporary workflow. So an attacker will wait for the perfect timing, retry this entire cycle, and then go again with the MFA fatigue attack. The second is SIM swapping. So SIM swapping is basically social engineering your carrier. So once they social engineer your carrier, they have your credentials, they have your number, they'll basically ask you to confirm your MFA by sending you a push notification. And in this case, the same thing, once the SIM swap attack is successful, it grants unauthorized access and your account is compromised. The third is social engineering. So this can be direct help desk attacks, manipulating the help desk and your support staff into resetting MFA through convincing impersonification. So in the same case, once the help desk is convinced, and they get unauthorized access, and the account is compromised. The third is real-time phishing, and this is proxy-based phishing attacks with credential harvesting, so something like Evil Engine X, like I mentioned. And they capture MFA tokens directly as a proxy, and once they get access, they basically have unauthorized access granted and the account is compromised. And the fifth one is malware session token theft. So in this case, this is like the nuclear option. You steal browser cookie sessions, session cookies, post authentication, and MFA here would be completely irrelevant as they would hijack your already authenticated session. And the conversion point over here, as I mentioned, is whether through user fatigue or technical bypass or through human manipulation, they all lead to the same place where access is eventually granted and your account is compromised. And attackers will try either a straightforward path or all these paths simultaneously to compromise a user. So what does a real attack look like? In this case, we all know, or you might have seen, we had an attack which was Octopus. And this was a real life attack which happened to multiple different companies, across the spectrum. And the attack basically was in August of 2022 and had over 10,000 accounts compromised, over 130 different companies. And what makes this attack super special is not its sophistication, but its simplicity. So they took everything I just showed you in that workflow and executed it at scale with surgical precision. So the attack is initiated. It starts with a text. It can be, in this case, Cloudflare IT. Hey, we want to compromise. Your schedule has been updated. Please log in to confirm. And this is sent to your IT help desk or any user in this case. And as you can see, the link over here, it's Cloudflare-Okta. And it's not a real Cloudflare domain, but it's impersonated. And when this attack is happening late in the night, you really don't care at that point. So eventually, the victim gets spammed, and they get spammed, and eventually they get to a point where they finally click the link on the phone, and they're routed to Okta page, so your Okta login page. And in this case, the interesting part is when you do this through your mobile browser, mobile browsers hide most of the URLs. And the page loads, and the genius part is it looks exactly like the Okta login page. So they basically clone the CSS, they clone the fonts, the animation, and even the favicon in this case. And the credentials are captured, and they're routed through an app like Signal. If you may ask, why Signal? So Signal is an encrypted messaging app. It's routed through Signal in this case because it's real time, it's encrypted, and it leaves no logs. And that's the most important part. So attackers in this case are literally watching your keystrokes appear in their Signal chat. And the MFA bypass here is brilliant because at the same moment that you're typing your password, the credentials are relayed through Signal, through a webhook in this case. And once they have this, you send your MFA directly to the attacker. Within minutes, they're typing your credentials, and at the same time, it takes less than 60 seconds to compromise. So total time to compromise is under 60 seconds, and the outcome is that now the attacker has a valid session into the real Okta. And they download your session cookies and then pivot to different applications. And then basically it's game over from there. And this is done at scale. So this can be done to multiple different users across the company. This can be done to everything, multiple users across different companies. And this is what the basic phishing kit code looks like. It has 20 lines of code where they're trying to relay credentials through Signal, and they're capturing user ID, password, your IP address. This is a basic demonstration, but they can capture much more information based on a phishing kit code. So because of this, the elephant in the room is that when you tell leadership that, hey, within the organization, I have MFA enabled everywhere, it's like a checkbox that's been tick marked, and everyone thinks that, hey, the account takeover problem has been solved. And well, the truth is, MFA fatigue is a real thing. And we've all been there where, hey, we're getting different messages or emails from different attack vectors if there's a data breach. And this brings us to two sides of the coin, where one is a technical vulnerability and the other one is human psychology. So what is more important in this case? And everybody thinks that, hey, once we have certain protections or we add a tool, that we've solved the problem. But really, the false sense of security comes where we don't take into account the human psychology piece. And that's where the account takeovers and the attackers win, where the human psychology is a greater threat than the technical vulnerability. And because of this, it brings in complacency and it ushers different security gaps within the organization. So the critical gaps that I've observed repeatedly is number one, due to this, there's reduced vigilance across the company, where we have MFA, people think we have MFA and we're good, but security teams stop hunting for anomalies. Number two is there's no post-authentication monitoring. All the monitoring is happening at pre-login phase or the login phase. And we assume that they're legitimate and we don't really monitor any traffic post-authentication. Number three is we do not have a proper incident response. So we're monitoring stuff, when we're monitoring stuff at pre-login, we check basic logs. Hey, we've logged in from this IP address. We're not really checking anything post-login, and that is what brings a weak incident response, where if MFA is bypassed, the team panics because if plan A does not work, there's no plan B. And fourth is there's a single point of failure. There's an over-reliance on MFA in this case, and when it fails, everything fails. So if MFA is not enough, what makes Google Workspace such an attractive target? I'm going to talk about Google Workspace over here primarily. So in this case, Google Workspace is a huge primary attack vector, and once an attacker compromises Google Workspace, they're basically in your app. They're in your organization. So for most organizations, Google Workspace is their business. They have emails, documents, calendars, Drive. It's where all the work happens, and once you compromise it, you basically own the organization. And I'm going to show you exactly how this works. So if your organization uses Google Workspace, this is for you. So Google Workspace isn't just a target, it's the target for an organization. And attackers prioritize Google Workspace is because number one, it's a single identity that controls everything. So it controls your email, your docs, your Drive, your calendar. One password basically rules it all. Number two, it's a data gold mine. Every contract, every financial doc, every operation plan pretty much lives in Google Workspace. Number three is admin privileges are nuclear. If you get super admin by any case, it's basically game over. They control your entire organization. And the fourth point is OAuth applications to Google Workspace create permanent backdoors. Even if you reset passwords, the OAuth tokens consistently persist over time. And five is basically business stops without Google Workspace. Ransomware has become old news over time, but lock a company out of Google Workspace and you're in instant paralysis mode. So one account becomes your digital pandemic. So it's time to get tactical and learn about different attack vectors that Google Workspace may have. And this is not just theoretical anymore. These are things that I've observed, and some might be obvious to you guys, but others may surprise you. But all of them work. So number one attack vector in this case is administrative account. So we target different admin accounts, and it's a crown jewel for Google Workspace. Because super admins basically can bypass any security policy or can disable your MFA or read everyone's email, access files, create backdoors, modify anything, and even lock you out of your own system. It's God mode, basically. And targeted campaigns, the number one attack vector in this case is target campaigns. So they create fake Google email support emails, and you'll see these emails pop up like, "Hey, your admin account needs verification." It looks legit. It's has a custom domain. It's perfect branding, so it's very easy to fool users. The next is exploiting admin turnover. So you see that employee who's left 6 months ago, uh, their credentials are probably floating somewhere on the web. So you need to be aware of that. And the third is credential stuffing with leaked passwords from different data breaches or just seen or admin reuses password too often. And most organizations have way too many super admins. Well, the second is shared account exploitation. So you may have seen different accounts from info at something company.com or support at company.com. So everybody uses it and nobody actually owns it. And it's like leaving your house key under the rock and your entire neighborhood knows about them. And these accounts break every single security rule, from generic passwords to shared amongst entire teams with no MFA, and because it's complicated to use amongst multiple users. And the primary attack methods for this are no MFA enforcement. So because it's a shared mailbox, nobody cares about the risk. There's password sharing, which goes wild. So you may have seen sticky notes on the laptops or the desktops that have been just assigned, say support at whatever the password is. There's zero accountability for these different shared accounts. So audit logs show that, hey, support at company.com has logged in, but nobody knows who's actually logged in out of the 20 or 30 or 40 people. And over time, there's permission creep. So it starts with basic email access, but then that email, that support at company.com email now needs drive admin access. And attackers love this because it's basically unlocked side door in a house. So number three is mobile device compromise. And your phone is always logged in. It's always authenticated. It's like a pocket-sized gateway to persistent authentication sessions, and which can create continuous corporate chaos. And lost phones are basically equal to lost company data. And mobile devices break security models. Offline syncs basically mean data lives on the device, personal apps mixed with work apps, and like I mentioned, persistent sessions. And the attack methods for these are lost devices. If someone finds your phone and is basically shoulder surfing or targets unlocked phones, basically like something like grab and runs, uh, your company data is gone. The second is malware. So one bad app on your phone can steal authentication tokens. The third is BYOD. So bringing personal phones and having no segregation of duties, accessing work data. So no MDM, no control, no visibility. And the third is public Wi-Fi. So using your phone on a public Wi-Fi, there's no security, any chance of man in the middle, there's no VPN. Any attacker may see your OAuth tokens. And like I mentioned, mobile sessions don't expire. The fourth is Gmail as the gateway. And Gmail is not just email, it's basically mission control at this point. Every password reset, every document share, every meeting invite flows through Gmail. And attackers know this, so they know that, hey, when you do a forgot password for email reset, they know that they can compromise and they can view this information in your Gmail. And it becomes the skeleton to understand other accounts. And the attack methods for Gmail are primarily email forwarding rules. So silently copying every email to attacker at gmail.com. You will never notice this and you'll never see this. Smart filters is something that only forwarding emails with containing specific keywords, in this case, confidential or wire transfer or contract. And this creates surgical precision, saying that, hey, I only want to see certain things or view certain things. There's delegation abuse, which basically grants delegated access to anyone in the company, and they can send emails as you. And the third is weak protocols. So these are old protocols like IMAP and POP. They bypass weak and have weak security. They bypass web protections. So anything, a simple scenario would be pull mail via something like a Thunderbird client. And email is reconnaissance heaven. Once attackers understand your operations, they can go after anything. The fifth is Google Drive. Google Drive is an attacker's all-you-can-eat buffet. It has a sharing model which is too easy. One click shares entire folders and entire trees under any hierarchy. There's the anyone with a link, which means literally anyone forever. The links never expire, even if the employee leaves the company. And the attack methods for these would be bulk sharing. So right click, share the folder externally. There's a 10,000 to how many ever files that can be exfiltrated within seconds. And the second is anonymous links. So the one I mentioned with anyone can view these links, share them via an encrypted channel like Signal, completely untraceable, and it can access your data. The third is version history mining. So in Google Drive, you may have seen there's multiple different versions of the document. So even if you delete the main document, you can still view the version history of the document. So you can get access to, attackers can like those things. And there's raiding shared drive. So you may have seen, a target drive, which may have seen shared HR data or shared, security team data. So they have a record of every employee record, and this can be shared, which violates, DLP rules, and there are terabytes of data that's gone. The sixth is Google Calendar, and Google Calendar in plain sight seems very harmless, but it's an intelligence goldmine. Calendar pretty much exposes the org structure from meeting invites to who are key decision makers, to when people are traveling, people who's attending conferences, etc. And the attack methods for this are social engineering, from what we saw before, and attack mining. So basically, they're trying to trick the team and see when the security team is on vacation. And the seventh one is OAuth applications. And OAuth applications are a Trojan horse here. OAuth tokens are basically gold tokens. They survive password resets, bypass MFA completely, and they basically last forever unless they're manually revoked. They create a persistent backdoor as a service. And the attack methods for these are, number one, OAuth tokens can have excessive permissions. So an email signature app wants full drive access, which is a big red flag. There's token harvesting, so steal OAuth tokens using malicious extensions, proxies, phishing kits, via info grabbers, man-in-the-middle attacks, and they can access the APIs forever in this case. The third is cross-tenant access. So compromise one org's application, and then you pivot to another org's, customer data. And there's silent exfiltration. So using a background API calls under a certain rate limit, and you're basically not triggering any alerts at that point. So what does an account takeover timeline look like in this case? So we start with initial compromise. In this case, this will typically last, it can last somewhere for 24 hours to 48 hours, and it's methodical. So it starts with some form of phishing, then there's some form of harvesting credentials. They're attempting to bypass different MFA techniques. It takes minutes, sometimes hours. But most attacks fail here. But the question is, once they succeed, how do we move to the next part, which is reconnaissance? So Reconnaissance leads to mapping your environment and understanding what exists. So data, accounts, privileges. In this case, they all work in parallel. And then there's establishments where attackers are trying to target different admin domains, different admin accounts while preparing for lateral movement, and this is orchestrated. And once the compromise is established, in this case, we move to the next phase, which is basically exploitation. And this is where the damage happens, where we look for parallel operations. So bulk data theft, while escalating admin privileges, email forwarding, while creating backdoor accounts, mining for calendar intelligence, while modifying security policies. And it's a coordinated assault from all different multiple fronts. So this phase typically runs for days, and terabytes of data can be downloaded, policies can be weakened, persistence can be embedded. And attackers are not just trying to steal, but they're also making sure that they can come back. The next is detection window. This is where security teams are trying to find different things. So we're noticing, alert fatigue in this case. Can your SIEM or detection and response tool, is it making too much noise? Is it going under the radar? We want to look for unusual patterns, which can get lost, in the flood of attacks. And by this time, you realize it's a breach, and they've been inside for a week, the attackers, and the company or the security team is doing a damage assessment of this case. So what is going wrong? How bad is it? And can we stop it? And the third phase of the attack timeline is recovery. So eventually, once you're able to detect these, how do you recover systems? How do you recover systems in the organization? And it depends on the level of compromise in this case. But immediate actions here include the account remediation, means auditing every account, policy hardening, closing gaps which have been exploited, and user re-authentication and session resets. So forcing everyone to prove that they're legitimate and thinking company-wide password reset days. Well, this is IT chaos, of course, and from this, we move on to lessons learned and how do we improve certain security gaps that have been established. This phase comes with a lot of cost, reputation damage, and data loss. And what you would see here is that eventually recovery comes at the cost of pain and not from actively looking at stuff. So that was all about the attack timeline and attack vectors. So I want to talk about defense and what does a defense strategy look like. So our defensive mindset needs a layered approach. And according to me, there are 4 layers of defense. So the first one here is zero trust architecture. Normally, zero trust architecture, by definition, is never trust, always verify. But it depends from organization to organization. Some organizations literally mean never trust, always verify. Some do it where we trust the users, but we still want to verify every activity within the organization. And this depends on culture of the organization. So every access, every time, every requirement. Second is advanced authentication. So beyond passwords, beyond basic MFA, we want to go to hardware keys and biometrics. So we'll discuss this in more detail. But the third is OAuth application control. We want to stop the app sprawl within the organization, and every permission in this case could be a potential backdoor. And the fourth is limiting blast radius. So making sure we compartmentalize everything. And looking at this structure, this can be a centralized fortification where zero trust catches anomalies, hardware keys prevent bypass, OAuth control blocks persistence, and we are limiting the blast radius. This is not a checklist, by the way. It's basically a system. The first part of zero trust is identity verification and behavior verification, where it's like having a bouncer at the front of your door. And here we're trying to do basic defensive methods like continuous monitoring. So we're monitoring not just at login, but at every API call, every file access, every minute. Uh, and authentication is a process, not an event in this case. The second is baselining normal behaviors. So what does John usually log into from what device and from what location? And we want to flag anomalies. So basically making sure that bulk downloads are not happening. We're not seeing new devices randomly pop up. And zero trust also needs context. So that moves into our second defensive method, which is device and location intelligence. And this is super important, where your laptop basically cannot teleport anywhere, unlike what they show in movies. And device intelligence catches impossible scenarios. So device health checks, is your device patched, encrypted? Are you running endpoint detection response? Any jailbroken applications or devices in this case? So hardware fingerprinting, where they're having proper asset logging and tracking. This can be serial numbers, device IDs, the installed applications, browser configurations, etc. And location intelligence. So if you see an executive location from San Francisco to, for example, say Singapore in an hour, that possibly can say that, hey, this is probably impossible travel detection. The third defensive method here is risk sensitivity and risk analytics. So a risk depends on different security levels and different levels within the organization, how risk is classified. So basic defensive method here is resource classification. So you tag your data and this can be different methods of tagging or classifying your data. This can be basically public, internal, confidential, secret, etc. There's dynamic risk scoring, so have a level of risk scoring. This can be based on multiple different factors. So a CEO accessing payroll, is that really something that we need? Or an employee getting access to financial records in this case. And then there's adaptive control. So low risk gets seamless access, and high risks need a step-up process or step-up authentication workflow or an approval workflow. Well, the next method is advanced authentication. So in this case, we're thinking beyond MFA. We're thinking beyond SMS codes. We need an auth which cannot be phished, which cannot be swapped or fatigued in this case. The first method over here is hardware keys. So your physical device is integrated into PKI, cryptography, and it cannot be phished. You always verify the actual domain. There's web authent support, which is, you can use FIDO keys over here. And this works on mobile too. And the key point here is FIDO 2 is phishing proof. So users can't accidentally give it to attackers because there's nothing to give. And the key does a cryptography handshake. So the important note here is that FIDO 2 does not work everywhere. This is why a strategy is more important and different methods to scale. I'll show you what advanced authentication would look like with hardware keys. So this is the first approach where it's a simple direct integration. So you start with FIDO 2, hardware keys, and you get access to different applications within your organizations. This can be SaaS applications. It has a limited reach, but it has an immediate security boost for critical applications in the organization. So it's good for a pilot program. The approach two is centralizing your apps and your identity with SSO. So this is a better approach where you centralize through single sign-on, and FIDO 2 basically authenticates to your identity provider and handles the rest. And now you have access to applications and get FIDO 2 protection as well with SAML or OAuth. The third approach here would be to use a zero trust service. This is like a gold standard, zero trust proxy service. So FIDO 2 is at the front door, and everything flows through the zero trust proxy, and this works for SaaS and self-hosted applications. But if you want to go the full-blown security route, you can basically go with the fourth approach, where you have the user authenticates with FIDO2 or traditional MFA to your SSO. But the magic here is the zero trust governs policy on itself, and this is based on intelligence done by the zero trust service. And then based on that, you can have a level of security with, if you have critical assets, it can go through FIDO2 security keys, or if there's applications for regular users, you can go through WebAuthn or different MFA techniques. And finally, we have OAuth application control as a defensive method. Here we have the different methods over here is having a pre-approval process. So before any application gets installed, have a security review done by your IT team or your security team. Who needs these applications? Why do they need it, etc. So have continuous monitoring, as we want to make sure we're monitoring every application via the Chrome management, and want to make sure that apps don't behave differently after a while. And basically have regular audits. So have a biannual or a quarterly audit. In this case, making sure that not every employee gets access to everything. And we're also monitoring different permissions. So we want to make sure that the application does not creep in permissions, or there's no application sprawl in this case. And we're trying to limit blast radius. So having least privilege across every application, having different trust boundaries, creating multiple different security zones, so that prod developers cannot touch staging, devs cannot touch prod in this case. Regional offices don't connect to global financial operations. And then there's session management. So don't just check at login, have continuous monitoring, check for anomalies, etc. I'll show you an example of how we can limit blast radius. So there are different tiers in this case, and the first tier is the red tier, where we're having maximum security because they're probably the most important in the organization. These are your C-suite. They go through hardware keys. The yellow is the super admins, or the department heads in this case. They're still very critical, but they need operational flexibility. So having strong controls over here is important, but not restrictive. And then the orange tier is where people can have standard security, your engineering, HR, sales, marketing, having baseline protections, location policies, having active monitoring. So when sales gets compromised, they don't touch finance. And when HR is breached, C-suite is safe. And finally, at the end of the day, we want to make sure that technology alone is not enough. We need the human element. And all the tech in the world fails if your people are afraid to speak up. And we want to make sure we have a security culture where there's no blaming and no shaming. And there are 4 pillars to this, where we want to make sure that there's no punishment for reporting. So when a user reports a phishing email, we want to make sure we thank them publicly, making sure what activity has been monitored. We focus on systems and not people. So we want to make sure fixing the process and not blaming the person. We share different lessons widely across the company of different phishing attempts, and if you have hands-on, all hands at your companies, you can do that. And we want to celebrate different reporters. Have a monthly security hero reward, having gift cards across, and your users are the first line of defense in this case, and probably the best detection system. So only if they trust you, they'll have the best security. So you build trust, and then you build security. And yeah, that's pretty much it. Thank you for your time. You can connect with me to whatever. Just final minute, any questions from anyone? Oh, yeah. I can post it for you. If you can reach out to me on LinkedIn, I can share it with you. Yeah.
Why we need this card like just Just we need to check if mic works. Yeah, sounds good. So, the blue team. Hi everyone. Today I will be giving a talk, AI in Defense, finding high value automation across a blue team stack. Um, so, my name is Adelia Brajimova, and I'm security engineer. I work for EPAM Systems, at a global consultancy and a product development company, and I'm currently focused on developing AI-driven solution for MSSP environments. So this talk will cover how to integrate AI into SOC, into Security Operations Center. Let me quickly walk you through what this talk will be about. So we will set the stage with AI theory foundation. I'm not going that deep into academic stuff, but just little focus. And then we will move to detection, rule creation, and translation section. And here I want to show how we need to automate AI and by using AI translation for detection, rule creation, and translation. Then we will move to detection log analysis section. So there is AI, I think, becomes more really interesting because everybody knows that machine learning is strong at spotting anomalies statistically. But while LLMs brings interpretation and a context. So I will show you how we could combine these two approaches. And finally, I'm gonna cover tier 1 automation. So tier 1, that is a part of Security Operations Center. And people find this job the most exhausting. So because of endless alerts and repetitive stuff, checks and tasks. So, and here I want to show how we need to use AI agents just to offload this work. AI theory foundation. We could broadly categorize AI approaches into four fundamental types. So RAG systems. RAG systems are class of AI solution that combine generative model with retrieval over trusted sources to deliver answering grounded up-to-date facts from both internal and external data. So RAG systems combine corporate knowledge base and threat intelligence feed to generate fact-based detection rules. And we have supervised models. That is a classical machine learning part. So supervised models use gradient boosting, classification, and anomaly detection, but on labeled datasets. So supervised models rely on labeled datasets and typically use techniques like gradient boosting and classification. AI agents. AI agents, data system that wraps an LLM with a state, tools, and policies. So it can perceive, decide, and act towards a goal iteratively and autonomously. So for, AI agents could be we could use for security operations center as a copilots. So these copilots actually could do automating triage, enrichment, and correlation tasks. And LLMs, of course. So modern LLMs like Llama, Mistral, GPT class models, they could build in the security operations center as universal automation layer. Let's start with detection rule creation translation. So before diving into solution, let's be honest about the problems we face in security operations center today. Adopting best practices is slow. So rules from communities, detection rules from community and from vendors often use a different syntaxes. So instead, just of reusing them, analysts spend hours to adopt them. So that slows down the adoption of best practices. Then it goes so analyst time is wasted. So here, highly skilled expert often end up with rewriting queries instead of just focusing on actual detection logic or improving coverage. Then it goes inconsistent detections. So without translations, the translation of detection rules, so the same detection pattern can look different across tools. So that creates blind spots. One CM might flag an attack, another CM just could miss it completely. And that is, and finally, all of this lead to vendor lock-in. So detection logic tied to one CM platform, which makes migration long-term flexibility much harder. What the best approach to address this problem? So that's an evolution. The answer is not just LLMs, right? So that's about an evolution from LLMs to RAG and then finally to RAG agents. So how this evolution happens. So LLMs are powerful, right? So, but they're not enough. So, because they can hallucinate and they don't know SOC-specific syntax. So, and there the RAG comes in. So, the retrieval augmented generation allows to bring in the field mapping and syntax example from index sources without retraining model every time. So, with the retriever finds the right chunks and the LLMs organizes them, and they get structured fact-based output from RAG to RAG agents. So, but the real breakthrough happens when they add agents. So RAG agents go beyond just retrieving information. They validate syntax, they understand SOC context, and they can even trigger a real-world action. Like updating detection pipeline or pushing a new detection rule into production. So that's the step from passive assistant to autonomous detection engineering. So here I want to cover a real possible architecture of agentic RAG AI rule translation from YARL. So the key moment here is a doc search that starts from this part. So instead of single retriever, system using a tooling arsenal of specialized instruments, as usually agents do. So security document retriever searches official UDM documentation and correct field mapping. GitHub rule finder, so on this scheme that just GitHub on the in the block. So the GitHub rule finder identify examples of detection rule, and then the Google rule validator check syntax and production compatibility from the official API and the field converter tool. So handle precise information between SPL, KQL, or YARL queries with multi-layer fallback strategy, just to guarantee valid results. Tools are selected dynamically depending on the context. So, for example, SPL or KQL and supported by semantic search that automatically categorize the detection roles, if it goes AWS, Microsoft, and etc., for more accurate matching. And together, all of these instruments ensure that agent doesn't just generate, but it retrieves, validates, and deliver output as and act as professional production grade quality level. So how we solve this problem? So that they build a RAG agent. So we shipped a production RAG agent that use a hybrid retriever and agentic plan to detect the source CM. So that is not just detect the source CM, that translate to a target and validate the API. So it runs in GCP and Azure as a scalable pipeline that converts a large batches of roles into production-ready output. So there is a link, guys, that you could just try to scan. You will find an article that I was an author of this article. Yes, there's supposed to be like thorough details, so please just follow and you will find this article with our RAG translator. Yeah, so we could move. But again, we still have pros and cons in this concept. So the pros, again, is that the speed, consistency, quality, reuse, maintainability, governance, knowledge growth, lower manual load. But again, the cons is that could be semantic gaps. We still have a corpus dependency. They still have a tooling feed and etc. Detection lock analysis. Again, really interesting part here. So the main problem that we have if we would like to work with detection, that is unstructured or noisy logs, that is, again, time-consuming investigation, that is real lack of correlation across sources, and that is high false positive rates because of insufficient filtering leads to alert fatigue. Yeah, and then the most vendors talk about AI for detection and log analysis. The default answer is machine learning approach. But there is a problem. They all seen by now that user and entity behavior analytics, probably everybody knows about this user identity, behavior analytic approach for anomaly detection, but it didn't live up to promises. So it tends to still generate high false positive rates. It still has lack of necessary context for analysts to make a decision, and it doesn't adapt quickly enough for evolving threats. But because it's still a machine learning approach, that definitely does shine in certain areas. So that means it very good at finding anomalies in large volumes of structured numeric data. So it builds statistically baselines, clusters, and applies time series models. And yeah, but if you're monitoring network flows or logging patterns at scale, machine learning approach is incredibly effective. But we understand that as machine learning alone is not enough, and LM alone aren't precise. So the answer is just combining them. So again, I was talking about the strength of machine learning. So it's great at the scale. It isolates outliers, detects signal spikes, and spots rare behavior and structured data. But machine learning still struggles with a context, and that's where LLM comes in. So LLM can interpret cluster and explain machine learning outputs by using logs, playbooks, and business context. So they add explainability and precision. So they tell you not just that using logs, that something is unusual. That's why it might matter. And here a possible architecture. So here was the full detection pipeline looks like. Then they bring machine learning approach and LLM. Here an example that was GCP based. So, and later I'll explain why the GCP cloud was chosen. And on the example, and everything happens with example of crypto checking log analysis. Yeah. So that's a good example also for investigation AWS logs. So that was really happened. So that was a crypto checking incident happened. And for example, if we have logs or if we intentionally generates logs for crypto checking practices. That was just an example with AWS Cloud. So because of that, we have as a data card duty logs, CloudTrail flow logs, and all of these logs go into BigQuery, be a pub and sub and data flow. Yeah, and here, future engineering. So from there, they generate hours, aggregates, counts, DNS, and IP lookups, hits or missing images. Then it goes machine learning detection layer. So in this case, that is a Vertex AI. So machine learning models we could use like isolation, forest, or Profit, or any clustering models for analyzing such logs. Then they also could combine these machine learning approaches, any machine learning models. We could combine them with LLM layer. That's the better approach is using RAG in this context, not just LM, that is RAG that enrich each candidate. So because we still have a context, and this output, the result written back into alerts table in a BigQuery and then routed to the, in this case, to Chronicle. So that is possible architecture, mostly about the GCP cloud approach again, but and here the reason why. So if we decide that's from my point of view, and if then I was doing the research, for my case, nothing beats Google BigQuery ML plus Vertex AI. because they still have SQL first ML that comes from GCP. We could work with seamless RAG on BigQuery logs with Vertex vector search. And here, on the next slide, there is a good table, competitive view on machine learning services. So there is a comparison between Azure, AWS, and Google. Here we have log ingestion, anomaly detection, triage, reckon logs, and from my side again, the best approach if you want to if you really want to completely customize your machine learning approach plus LLM, it's better to go with GCP cloud because of the services, because of the BigQuery, and especially if you want to work with pipelines, it's still better just to use GCP cloud for this case. Here, price overview. Yeah, so, and again, they still have pros and cons, this approach. Again, pros, that is speed, that is scalability, flexibility, that is continuous learning, because we could use models, improve them over time with feedback and retraining. Automation enables automated triage and enrichment of log events. But we still have these cons. So the cons, again, we are trying to analyze logs, and they probably could be sensitive ones. So data sensitivity, LM may process sensitive log and raising privacy and IP concerns. That is a false positives explainability. So sometimes complex models may produce results that's just hard to interpret or just justify. And again, so the main cons, that is security risk here. Tier 1 SOC automation. So the problem statement that they have, that is alert fatigue, skill bottleneck, inconsistent triage quality, and SOAR. SOAR is static. So alert fatigue. So analysts drowning in repetitive log value alerts, as I mentioned, so that the most exhausting job for analyst, that's a tier 1. So that is inconsistent triage quality, and from my side also that the main problem that the SOAR is static. So traditional SOAR platforms don't really solve this. So they really on predefined playbooks, they struggle with new willing threats, and the results a system that can automate the past, but not adapt to the future. Agents. So here again, the best approach to resolve this problem is agents. So multiple agents can take specialized roles, triage, enrichments. And if we really talk about AI agents, the best thing here is that agents could really act as security operation team. So instead of one giant model making every decision, we orchestrate multiple agents, and each agent does its part. So together that function like an AI-powered SOC team. So the result is scalable, reliable, and much closer how a real team works. Yeah. But from my side, the problem here, this approach, again, that because we couldn't rely on the agents as a SOC team completely, because they still need to have a feedback loop. We need to monitor them. We need to monitor them. And here is a possible architecture of this approach. So, so that all happens from ingestion. So we start with alerts that coming from CM platform. They enter the pipeline through a message bus, probably a queue. Then it goes triage agent. So the first agent in line is usually a triage agent. Then it goes enrichment agent. The agent pulls in the context that use threat intelligence, asset data, user info, and everything analysts usually have to fetch manually. Then it goes decision agent. With enriched alerts, the decision agent evaluate what to do, escalate or suppress or after close. And this decision agent, from my side, the most sensitive one, because there is on the better way to work with decision agent just to have end core mechanism, because we need to control the age isolation step until I've never seen in practice that decision agent was completely autonomous agent. Every time that usually works with end core approach. Case agent escalation agent, that is, if the alert is valid, a case agent creates the ticket with a full context. And the final step, that is a feedback knowledge base. So from there, analysts feedback loop back into knowledge base metrics and dashboards and track performance. So it all goes to the ticket and to the knowledge base. We still have here also pros and cons of this approach. So the pros are at the speed, that's quality, much better sometimes, that the consistency, maintainability, that knowledge growth, that governance. But the main cons still are, again, that is corpus dependency, semantic gaps, and it's false confidence, and sometimes that is drift upkeep. And again, security API, central KBA may expose sensitive detection of hit license issues. Here, the good schema that really shows us how SOC code looks like. Especially, I do like this alert triage and incident response part. Here you can see the alert triage agent, investigation agent, and incident response agent. They in one block. So we still need to have context enrichment. We still need to have SOC analysts that will control these agents. And again, there is no way to automate this agent without any feedback loop. Yeah, guys, do you have any questions? Mm-hmm. I really like this question. Probably everybody knows about Profit teams and our vendors that provide security automation solutions. And the problem is, mostly of vendors or security automation mostly focus on tier 1. And the answer is because it's easier just to handle the context about the alert, because the tier 2 usually focuses on not just covering all information. They more focusing on isolation, suppressing with real world actions. And here, the real problems, there is no way to have absolutely autonomous agents. We still need to have analysts. That's kind of end-on-core mechanism approach, and that's a real problem. So that's really hard for vendors or for products explaining people like, yeah, okay, you can use this automation, but we still need your analyst. And there is lots of problems, concepts, and questions that still SOC operations still just trying to figure out how we could use this automation in tier 2, because we still working with a sensitive logs. They still need to think about how how we could integrate AI, especially if we're talking about like integrating not supervised machine learning that was built on the sensitive data that's more secure than if we think about any open source models or famous GPT class models. If you want to integrate them, that's again lots of questions, pros and cons. Yeah, I'm sorry, probably answer for your question. Yeah, guys, do you have more questions? Okay, thank you for your attention. It was a pleasure to be here.
Thank you very much.
Hello, everyone. Uh, Good afternoon, and thanks for being here to attend my session. My name is Mrunal Gangrade, and I work for JP Morgan Chase. I am the into Identity and Access Management group at JP Morgan, and I am going to present a topic on multi-tenancy in the clouds. I hope you guys enjoy it. So I will start with the introduction and motivation, then the threat landscape. Then I will move on to the technical isolation, monitoring and policy, case study, and then the best practices. So the first is defining multi-tenancy. So before we were introduced to cloud, each organization had their own infrastructure. That is pretty old now. Like they had servers across locations. They had servers in the northwest and the middle west. So if anything goes wrong with one data center, then they had the disaster recovery in the other data center. So it was it was their own infrastructure, which was secure. Obviously, no one can enter that infrastructure, and it was slow, but it was still secure. It had its own challenges, but the one thing about it was that it was secure than the way cloud is now. But moving on, like we got introduced to cloud, and then slowly all the organizations started moving to clouds. So as you all know, like cloud is pretty expensive. Like you can't really have your own infrastructure inside cloud. Then it will beat the whole purpose of having business or whatever. So the thing is, when we move to cloud, there are various benefits of it. It is cost efficient, it is scalable, and the production environment, if you need say for the banks, if there is, or Amazon, if there is an Amazon deal day, it can easily scale up the servers from 10 to 15. So the scalability is achieved within seconds, and that is the benefit of cloud. When all the companies started moving, and then they all started having the benefits of cloud. But with that, there were also challenges. For the first is because of the cost effective, everybody, the cloud will give you one environment, and then multiple organizations or even multiple hosts have to deploy themselves on a single host. So that is something which is called as multi-tenant. So when the provider, say Amazon or even the Google provider, when they give you a space, that same space is actually shared by other organizations without your knowledge. You don't know which all organizations are sharing that space. You just sign one contract where you have defined some rules, and you assume that, okay, I'm going to get the security and privacy which I need. But that's not the case. Once especially in the organizations where the data is very critical, like cyber security, then we have the health and the financial. So that is very important, that if any issues come, or if anyone tries to attack the cloud environment, which is very easy because some other company has actually, organization or even the attackers are actually sitting on the same host where you have deployed your data or their application on that server. So that is the challenges, that strong need for data and execution isolation is one of the challenge which the cloud providers face in the multi-tenant combination. I will walk you. There was a very famous incident with Capital One in 2019. So there was a misconfigured AWS roles. They had the IAM roles, which identity and access management role, which was given like the most privileges. So the attacker they took advantage of the server-side forgery to actually get into the space of Capital One. And once they got into, they had the access to the S3 bucket. And they didn't stop there. Like once they had access to that particular S3 bucket, they started moving vertically and tried, and later on they had access to several S3 buckets. So that happened because, the main rule of IAM, identity and access management, is the least privilege, the rule of least privilege. So that was not considered by them because I guess that there was a break which the attacker found it, and then that's how they got into the Capital One. So that was one major attack which happened in 2019. So if a big org like Capital One can have that attack, so no one is safe, basically. So that's the main point of this presentation. Then we also have the meltdown, and this is a real world breach, like hardware flaws expose secret between VMs. So what are like virtual machines? I will just start with the basics, like what are virtual machines? So in any big org, like where I'm working or where I previously worked, you don't get a particular hardware. Those days are gone. We get like the host is the same and they install some hyperware where you get virtual machine. So when you are working on your machine and in the office or something, you feel that it is you own that machine, but actually it's just space on the hardware which you have been given to. So the attackers, what they did was, like, since they were exposed to the CPU or the hardware, they found out the traffic on those memory on the CPUs and also the memory caches. When the memory caches happen, there is a lot of CPU usage. But so they found all those things by just like eavesdropping, like just finding the data and how the patterns are on the CPU. They were able to attack that just the hardware of those VMs. So why isolation? So it is like a very basic thing. We need isolation because it prevents data leak across customers. When you go into cloud, or when any org, when it goes into cloud, it expects or it assumes that the data is private, but it's not, because on the same host or same machine you will have several other services also deployed. So it's not really safe, but it is, we need isolation to prevent the data leakage. Also for the privacy, trust and compliance. So customers will need to trust the org in order with their data. So they need to, if any such incidences like Capital One, if they start happening like throughout, then the customers are going to lose their trust. So it's very necessary that you have the critical privacy trust of the customers, because ultimately the business comes from the customers. And then we have penalties from GDPR or HIPAA, or even the finance industry is all regulated. So it's not only about customer trust or data privacy. Companies have to pay billions of dollars to, if there is any breach in the security of any data leakage. So even for that, they have to make sure that their data is protected in the cloud. So that's why, like, we really need isolation. That's the motivation. So threat landscape, how leakage occurs. So misconfiguration, IAM and buckets. So after it goes to cloud, if you're aware of how AWS works, the main thing of AWS is identity and access management. You can define policies, you can define rules and assign it to the accounts, humans, roles, you can have all that. But the rule what everyone should follow is rule of least privilege, like deny everything by default. So even if someone tries to get or already got into your network, but it is denied by default until they assume some roles. So that will be difficult for them to assume. So the leakage occurs, for example, with Capital One, because the IAM role was misconfigured. That was the reason that the attacker was able to get into their network. So misconfiguration of IAM roles is the main reason why the threat occurs. Shared resources like CPU or memory, if there are more containers also on the same shared resources, then the eavesdropping can happen. You can also, the attacker can find out when is the load more on that particular business and try to load the system during that time. So actually the system will come down. So shared resources, memory resources, CPU and memory resources shared are the main cause of the threat landscape. As I already mentioned, like side channel exploitation is actually eavesdropping, where you actually try to listen to the CPU and memory usage of another application and uh, try to find, like, the attacker will get the insights into when the attack should actually happen, like when is the password caching is going to happen, because during that time there will be like several cache, the CPU usage will go high when the caching actually happens. So that is one of the reason that is one of the example of side channel exploitation. So these are the main reasons why the leakage occurs. Common attacks are VM escapes, where the attacker will find a way to get out of the VM and go to the host. So it has access to other VMs on that particular host. So these are very common attacks. Container breakouts is similar to VMs breakouts. Like the attacker will try to get out of the container onto the VM, so they can have access to other VMs on the same containers on the same VM. Timing and the cache attacks. That is the example of side channel exploitation, where the attacker will actually eavesdrop on the memory usage and cache timings to get into the system. So these are the threat landscape. I'll move on to the detailed threat time. VM escape, breaking out of VM at the host level. So we have a host where we have several VMs on that host. You can think about an example is like you live in an apartment complex. So your host is the entire like the building, and the VMs are the apartments on that building. So say a burglar or someone tries to get out of one apartment and goes and somehow gets the access to the main room. From there, it can actually go get the keys for all the other apartments and get into it. So think about the VMs at smaller apartments and the host as the whole building. So one building is actually hosting several VMs. So if one burglar tries to get the access to the main room, then it can actually get the keys to all the VMs. So this is just an analogy, like for the breaking out of the VMs on the host level. Second is escape from the container to the host. It's a similar one, it's just at a smaller level, like VMs, host are having VMs and VMs are having containers. So if the attacker gets out of the containers and onto the VMs, then it can get access to all the other containers. So it can then attack the memory or CPU of those VMs, and it's again a security breach. Side channel is leaking info via CPU and cache artifacts. So in reality, like at least in the applications what I have worked on, the caching happens, like all the credential cachings or whatever happens during certain times of the day. It's not like every time when you go and log in into your system or any critical system, it's not like it goes and gets your credentials or whatever your roles or from the it just matches something and then it gets it from the cache. But there are certain times of the day, as per of whatever is the policy defined, that the caching will happen every 5 hours or 4 hours. So every 4 hours, like, if you have some, for example, if you need to access a external website and that website gives you a token. So you cache that token for 4 hours because you know that after 4 hours it's going to get expired. So caching happens on every system, and the cache is refreshed also like timely. So if the attacker finds out those details as when the caching is going to take place or when the cache is going to get refreshed on the system, then that's going to help the attacker to get into the system. So these are the detailed threat types which happen on normal whenever you deploy your application on cloud. So cloud service model, there are 3 types. One is the software as a service, that is SaaS, then platform as a service, and infrastructure as a service. So software as a service example is like your Gmail, that is a software as a service which you use it, or Salesforce which you use it. So you're not deploying or doing anything with it. You're just using that service. But the security lies with the provider. So if Google has an issue, and if it tries, if for some reason the one customer's data gets, exposed to other customer data, then that is, everything is in cloud. So that is a data isolation, and that is a data breach at the software at a security level, software as a service level. So you can take the example of Gmail or Salesforce or whatever apps you use. They are all software as a service. There are organizations which are providing you the software and you're using it as a service. So they all come under software as a service. But they take care of their data isolation. Like your data is not shown to another person, or another person's data, you cannot see it unless you are explicitly given rights. Example on Google Drive, like you can share it with more than one user. So that's an example of software as a service. Platform as a service is mostly which we use to build within, like as developer, I'm a developer, so we use it to build our applications. So we use, like, if there is any platform, we use the APIs to build our services based on that. So the breach can happen at API level. You can, as if I'm the attacker, I'm going to try to configure or try to attack the API in such a way that I get out more information out of it. So if the API is not properly secured, like, I can just get, for example, an API, just, it's a very basic example, but if the API is not using any credentials of a role or something, so once you, if I, as a developer, I should not be able to access the HR data because I'm just a developer. So I should have a role assigned to my ID. But if that is not there, so once I get into the system, if I can access my data, I can access the HR data also. So it is very important that all the configuration is done properly, so you don't, like, the attackers don't have that benefit of, all these misconfiguration which happens in platform as a service or software as a service. Then the last is infrastructure as a service, which is at the very basic level, where the EC2 instances, the VMwares, the host, everything is infrastructure as a service, where we use the AWS EC2 instances and we deploy our applications. So the configuration is totally the responsibility of the org which is deploying the application. The configuration of the infrastructure is not the much responsibility of the provider. So the responsibility lies with the person. For example, the first one, the SaaS, that is software as a service, Google might be deploying their services on infrastructure. They might be using infrastructure as a service. They might be using EC2 instances to deploy their application, where you can use the Gmail. But the configuration, how they protect their application from the misconfiguration, is totally their responsibility. So there are 3 service models, cloud. Only if you are, like, working as a developer or something, you really get into, like, infrastructure as a service, or else mostly it's like, software as a service switch. So we have the hardware isolation. There are 2 types. One is virtualization and second is TEEs. So hypervisors isolate VMs. So every hardware, like once you try to isolate the VM, there are hypervisors. So hypervisors will actually isolate the VMs from each other. So as a user, you don't know, like, it is actually multiple VMs on the same host. But as an attacker, you know that there are multiple VMs on the same host. So you can have, like, the phishing becomes very easier in that case, because you can actually attack a system, because as an attacker, as I know that the hypervisor is actually isolating the VMs. I can easily get into the other VMs if I get into the host. So as an attacker, you know that. So there is Intel SGS and AMD SCV. These are 2 services what they provide. So in that, you can safeguard your data. So what I can, just an analogy, even if a burglar breaks into your apartment, but if you have a safe lock, they still can't steal your data or your important things, because if they break into your apartment, they have to get access to the safe lock. So if they cannot get access to the safe lock, even if they break into your apartment, your documents or whatever is the important stuff is still safe because it is inside the safe lock. So TEEs are are an example of that, just an analogy. So Intel SGX is the one which provides that, and like it actually safeguards your data. So even if the attacker gets into your virtual machine, you can still safeguard it by using it. So this is one of the way, like hardware isolation, where you can protect your data. There are also other ways where you can do it is namespace and C group partition processes. So namespaces, basically, you know, like you define namespaces into your processes. So if there is a process, you know, running in namespace 1 and there is a namespace B, like think about it as like some groups, like minor groups into the container, which we create for isolation. That is all, there are VPCs, virtual private connection networks, and all that, you know, it is another level of programming which happens there. So you have those namespaces and C groups partition process, which will actually partition your processes. So even if like you have access to one process, for example, restart, there is a just an example, this is called simple Linux server, and you have like, you know, restart the process, restart the service, and also install the service. So if you have access for some reason, you got the access to restart the service, but the install service is still being safeguarded because it is in a separate namespace. So when the architecture is defined, you have to define in such a way that one process does not get access to the other process. Kernel capabilities restrict privileges. So all the VMs are basically like, you know, Linux, or they are Unix machines where a root user has all the access. So if you don't safeguard the root user, then you're going to be in trouble. If anyone tries to get into your Linux machine or your VM, wherein if they have the root privileges, then they can even shut down your machine. So kernel capabilities restrict privileges. So there will be separate privileges defined, that is read-only, write, executable. And whenever there is a process or a file, you can actually give permissions to that file that only root user will be able to modify or, you know, delete that file, or view that file will be to anyone who gets access. So by that, even if like, you know, attacker gets into your system, you still can safeguard it. So that's the whole way, like, you know. Next is like Kubernetes is the container based, which is very much popular now. So it uses the RBAC, that is, and pod security network policies. So it safeguards your application based on RBAC, pod security, and network policies. So we have a VPC, virtual private network, and anybody tries to there are actually rules defined, like who is allowed into your network and who is not allowed into your network. So Kubernetes is a very, right now it is in thing to have your applications containerized. So I was talking about network isolation, that is VPCs. VPC is like, you know, you can think about, you have your, like, previously we used to, like the companies used to have a standalone architecture or infrastructure for their own org. So that cannot happen in cloud, because now cloud is like, you know, many organizations share the same cloud. So there is a concept of VPC, that is virtual private cloud. So you define your own virtual cloud inside the bigger cloud where only your org can deploy the changes. So how that cloud is controlled? It is controlled by the IP addresses, the subnets, and the policies, like what is allowed into your system, what is not allowed, even the micro segmentation. For example, the database is the most important part. You will have to safeguard the database. So you have to write a policy in such a way that all the external requests cannot access your database directly. So that is micro segmentation inside your VPC. So those rules have to be defined, like the VPCs, the security groups, all have to be defined so that there is network isolation. So the main aim of network isolation is making your cloud as private as what you would have on your own premises. So that is the main aim of the network isolation. And software defined parameters, you can actually code your network by defining the policies, the parameters. You can actually give the IP address to where your network can be accessed. Not all the protocol, whether it's HTTP or TTA, the protocols you can define on the software defined parameters. So only the ones which are allowed will get into your network and not all. So once we implement that, the major thing is monitoring. We also have to monitor like how everything is going on into the system. So we have to enforce mechanisms. Also, where I would just, even though it like from my real world experience, this is where the AI comes into picture. So because humans are not that equipped to identify abnormal activity, and that's where AI is. Suppose like AI can actually detect that there is a person who has downloaded at 3 a.m. 200 documents. So nobody can actually monitor that except for like AI. It will be easier. Then AI will give an alert to everyone that this is what. So monitoring is where AI can actually help everyone. Regarding the capital one, the monitoring and the alert was the example what I shared at the beginning. The monitoring and the alert was not that equipped. That's the reason the attacker was able to get into other S3 buckets. So if there was a monitoring or alert during that time, they could have stopped the attacker. So monitoring of the network once you set up is an important step of your cloud security. So there are three main things. One is runtime monitoring of boundary breaches, like continuous surveillance of system to detect unauthorized access attempts, or if anybody even gets into not normal behavior. If the AI detects, or if anyone detects, like is the normal example is like if you try to use your credit card in some other country, you do get an alert like, okay, your credit card is being used. So that is part of monitoring. So that is how it prevents the threat, or that's how it prevents the attack. I mean, it will just try to find out, okay, it's not you, it's not the correct, I mean, it's not the usual location where you usually swipe your credit card, is being swiped in another country. Is that you? And then you'll have to verify several things. So that is monitoring. Like we have to, all the orgs do it. Once their application is in the cloud or not in the cloud, monitoring has to be there. Then identity and access management and the cybersecurity, they all work together. So rule of least privilege, deny everything by default. So even if an attacker gets into your system, they will get denied by default unless they have the privileged assigned to it or role assigned to it. The attacker will not be able to do anything. So just because you get into the system doesn't mean you have access to all the data. You will have to have access, you have to assume roles, and that's what all cloud is about. As I said, like the behavior analysis to detect threats. If someone is like at 3 a.m., if someone is trying to download like hundreds of documents, then that is definitely a threat. You will at least try to analyze that why someone at 3 a.m. is trying to do that, or the card is getting swiped in another country or at several locations in the midnight. So that is the behavioral analytics, which is part of monitoring and which will safeguard the application. So capital one, I guess I have already mentioned it n number of times during this, but that is one case study, the real world case study, that server-side request forgery attack took advantage of the misconfigured. So the APIs are an example of the server-side forgery where the URL is exposed to the end user, and they can actually, change the URL, change the permissions. You can directly hit the URL if that is not safeguarded. So that's the reason, like we safeguard the URL that only authorized users can access it, either by a token or someone. But these are all the server-side forgery which happened on the Capital One. Once inside, the attacker was able to you access extensive Amazon S3 data storage behind the initial target scope. So the gaps were least privilege, insufficient implementation, inadequate monitoring system, and delayed alerting mechanisms. So monitoring and alerting also plays part. So by whatever, like if at all your system gets attacked, it has to be alerted. Like the org or the owners have to be alerted that this is what is happening. So if that is delayed, then the attackers have more time to cause problem into your system. So monitoring and alerting is also one of the important points. So the lessons what we learned from the Capital One was that enforce least privilege, default deny policies. So this is a very important policy in any cloud, like default, deny by default. That is what everyone follows these days. That is deny by default. Just because you have an ID, doesn't mean that you have access. It's just like deny by default. In the beginning, all your access is denied. You have to explicitly request for access, and also, a policy of least privilege. If there is if you are part of two groups, for example, I'm just giving you an example. If you're part of two groups and one is denying you access to the same resource, then it is denied by default. Anything which is denied, it is denied by default. Then there has to be automatic scan, deploy automatic scanning tools like AI or anything which will work into your system, which will monitor it for you. And if they see any unexpected behavior, that will also, alert everyone in the org. And basically the goal is to establish 24/7 monitoring. Even when you're not looking, somebody is looking into it. So the future and the best practices is zero trust confidential computing. So we just have to have zero trust. Don't trust anyone. Automate the security poster reviews. Everything has to be automated. Even when you're not looking, somebody is looking. There has to be a 24/7 monitoring. AI-driven detection, which is very helpful, because humans have certain restrictions, which AI does not have those restrictions. So AI-driven anomaly detection is one of the emerging technologies. And then we have the RegTech for compliance mapping. We have GDPR, HIPAA, CCPA directly getting combined with the organizations. So they are regulated as per the whatever is their specifications. So they actually integrate with the organizations, depending on, like, if it is health, then they will integrate with HIPAA. So do you have any questions? Yeah.
I have a quick question, because I think it's something Alex deals with. There's a lot of tools like Polish, CrowdStrike, that you can actually put tools on the EC2 instance.
Yes.
To monitor and protect. The big issue that I think security is facing right now is with every K8, your Elastic Beanstalk, the dynamic application, then can't necessarily take those tools. Any suggestions on the best way to do real-time monitoring of those environments? Because a lot of times you have something deployed in an AWS and uses the VPC. You're doing everything you're supposed to. A lot of the time, you're waiting for Amazon to send you an email saying, hey, we noticed this anomaly. And just looking at a better way to do that, because the way a lot of the security tools are doing it now is they'll check the registry of the base image, but that doesn't mean that's really what's happening and running on the Kubernetes cluster. So like I said, just looking for suggestions or best practices for anything in your experience you could recommend in order to how to keep up to date with real-time monitoring.
Yeah, it is. This answer is based purely on my experience. What I believe is safeguarding your security at the base level, like your, the inbound policies and the outbound policies. That also helps, even if your application is containerized, but it is actually on the VMs or into your, the virtual cloud. So if you safeguard at the base level, that you actually have a control over who can access your application or who cannot access your application. That is one of the important thing which I feel. And regarding what the problem, what you said, I think we should really integrate AI, because that is like the real, we have the Gen AI and all. So that we should actually come up, at least for the finance industry, the models should be trained. We have a lot of models, like they should be trained based on the real time data. And the monitoring is something which the monitoring is something which we have to like I think that can really help with the monitoring, the genetic AI, if it is integrated.
The other question I have is just, when you're talking about PM escape, most of the attacks happen in hardware layer.
I think it's more on the virtualization layer. Yeah. Hardware is still easier to safeguard, but the other, like the exposing point of the virtualization is more like you have APIs, you have several exposing points, but hardware is limited. That information is not easily available to attack. Yeah, sorry.
So situations like that, with like DMX, how does an organization scale up under lack of visibility into things like that? I feel like most organizations that start using cloud, it's just that's considered inherited credits.
Yeah.
Running a production instance, it's hypothesized in some cloud data center, and we don't really have visibility into the providers' controls, their governance, their procedures, right? So how does your organization manage that risk?
Yeah, that's a very good question. I would just like to tell that my organization, I come from a financial background, just like healthcare and finance, they are the main business industries. They have not moved completely to cloud because of the same reason. There is still premises a lot, where the critical data or they are still there. They are doing a hybrid, but they have still not moved there. But the one which I can think is like my organization, they also started with their in-house cloud. So with in-house cloud, they were trying to, I would not say some of the applications are on the public cloud also, but then that is safeguarded by using the VPCs or having your own virtual private cloud. Yeah. Yeah. I think you had a question.
As case studies or exposures, you listed meltdown and vector. My knowledge, there's never been an actual breach using those. They're common problems in all modern CPUs.
Yeah.
CPUs, but my knowledge, it's never been breached or used in a breach. Wondering, you know, something different from me, and I've been in this industry for a really long time. So, I mean, has it been breached?
Yeah, I did. I mean, I don't have the exact I did have it when I was studying this, but I don't have the exact details of what happened. But I can get back to you with the details. There is like not on a whole level where you can actually, but that is a common point where the attackers try to get into the system.
Memory spaces, but yeah.
Okay, I'll take that point. I'll look into that. Yeah. Thank you so much. Yeah, I'll check that. Yeah, any more questions? Yeah.
No, I just wanted to make a comment on this gentleman's question. So, folks are all talking about that. CrowdStrike became quick sensor things and things. So, majority of the PR solutions have the ability to send many instances that are available. But also, but CSPMs also, you know, it also they use, for the but I did have a question. In terms of your like security program at your organization, do you concentrate more on the shift left approach, where you're breaking builds on, let's say, misconfig deployments?
He's from my org too. Do you want to answer that?
Or, I guess let me.
Yeah.
Or are you going
more into like production vulnerabilities where you're using CSP platforms.
Yeah, it's a hybrid approach. We're definitely thinking shift left.
Yeah.
So that brings the things to developers IDE and kind of solves the problem before it gets released to production. But that's journey altogether. Right?
Yeah.
So,
It's still like we are more on-prem. We are just moving there. But as you know, like finance is the most secure data, so it's not a complete shift.
Okay, but you do, I mean, are you blocking builds since you are trying to start
Yes.
like clean and fresh?
we do.
Yeah.
So you do, okay.
Okay. Anything else? Yeah.
Curious, in terms of all this, isolation and the breaches, have you noticed started a trend moving away from Microsoft hypervisors, Microsoft products towards Linux, like a large trend? Have you seen that?
From moving away from Microsoft hypervisors?
Ditch Windows and move to something else?
No, at least not I have. I worked with Citigroup and JP Morgan. I didn't see that trend there.
Yeah,
They're still there. Yeah, they're still there. This is my LinkedIn. If anyone has any questions or email, I'll get back to you. um, yeah. Uh, monitoring, AI-driven monitoring. For network monitoring, I mean, not that I'm actively working on that part, but I'm also a like independent researcher. So as per whatever is my research, I would try to, I mean, I would go with agentic AI and explainable AI more also because explainable AI is also becoming a larger trend, at least in healthcare and finance, because ultimately all the regulators want to know that how particular decision was reached. Like, for example, you can't just deny, like, if you put it more monitoring and say the agentic AI or someone just says that your card is denied, and if someone asks you like why the card was denied and there is no explanation, then it is. So I would go with a combination of agentic AI and explainable AI. Yeah. Yeah, that's a problem. That's why I guess we don't have more finance or healthcare yet moving to. That is the shift that is not happening actually in finance and healthcare. If you look at the overall trend in the industry, it is happening all over. But finance and healthcare and insurance are the three industries which are not moving that fast to the AI. Because it's like a black box. Once you move to AI, if you're not able to explain why it happened, then nobody is going to believe. And ultimately, the customers have to trust you. So the shift is not, in other industries it is, but in these three industries, I'm seeing that the shift is not that fast. Yeah. Are there any questions? Thank you.
Hello, everyone. Good afternoon. And thank you for joining us for today's talk on Design Like a Attacker and Build Like an Engineer. I am Shilpi Mittal from Tyson Foods, and with me is Ankit Gupta from Axeta Finance. We are here to deliver some talk about secure SDLC. So let's ground the reality where most breaches doesn't require a sophisticated zero-day exploit. All it take a weak trust boundary or a stolen token. That's enough for attacker to walk right in into our system. And our answer is very simple, but yet powerful. Design like an attacker and build like an engineer. Let's, um, uh, let's design like an attacker means by mapping trust boundaries, imagine abuse path, and set secure default. So gaps are closed before code ships. Design like an engineer means disciplined execution, enforce least privilege, design isolation, utilize automated checks in CI/CD, and plan for rapid recovery so that one mistake doesn't spiral into crisis. By the end of this session, you will know practical plans and a sheer vocabulary that help align development, security, and leadership. As we go through, we keep one question in mind. If someone is stolen a valid session in your product today, how far they can get. With that challenge in mind, let's look into the roadmap for our time we spend together. So we will start with reality check on 2025 threat landscape, the top attack method, and the vulnerabilities where they creep into software development lifecycle. Then we will shift into first theme, design like an attacker, and this is about putting adversaries' hat during design, threat modeling, secure defaults, and spotting abuse cases before code ships. After that, we will move into second theme, build like an engineer. This encompasses of discipline practices, automated tests, and release gates, as well as architectural patterns that prevent damages and resilience strategies that ensure system remain stable. We will also explore how AI is reshaping in 2024 and 2025. AI has become a double sword. It is a supercharging defender, but it also gives attacker new tools. We will look both sides of that. Finally, we will also look into future-proofing recommendations, a practical plan for you, which you can take away for your next steps. By the end, you will have a both clear picture, today's risk, and a modern framework for building software that defend itself. With that roadmap, let's dive into 2025 threat landscape. So first, let's talk about the vulnerabilities. From last year alone, over 30,000 new software flaws were identified, representing a 17% increase from previous year. Zero day was alone exploited within day of disclosure. If you remember the MoveIt breach in 2023, a SQL ingestion that hit dozen of organization almost immediately. Next is credentials. This is where the phase 2024 stolen credentials were responsible for approximately 30% of breaches on par with direct application exploits. And it's easier than ever. An active market of MFA bypass kits that are intercepting one-time code so that attacker can turn phishing campaign and dark web dumps into instant access. Then we have phishing and social engineering are still huge, roughly a quarter of breaches, but tactics are evolving, where we are seeing fewer generic blasts and more targeted campaignings, even AI-powered deepfakes. And finally, supply chain. These have rising more than fourfold in recent year, and analysts predict nearly half of organization will face one of that by end of 2026. Um, the model is simple: compromise one vendor, reach all their customers. SolarWind demonstrated devastating impact that it can have with 18,000 downstream victims. And then attacker do not even need to storm your firewalls. A weak link anywhere in the ecosystem or unpatched code or an stolen credential or insecure supplier opens the door for attackers. To close those doors, we need to understand where the software development lifecycle itself most fragile. First, we need to understand security is baked in, not bolt on, from very first blueprint to the final deployment. Security has be a part of foundation. Think like designing a bank. You plan walls and reinforce walls from the starting, not a structure you built and then try to patch it later with a lock pad. The same applied to software security. It must be architected into design, not slapped afterward. While designing, we actively put on their adversaries' thoughts. During design, we map trust boundary, imagine abuse cases, and close gaps early with secure defaults. For example, identity system might ship with MFA required out of the box rather than leaving customer to harden it later. Build a software or system mean discipline execution. We design for failure and containment. Think of an example like a watertight compartment in a submarine. So one breach doesn't sink the entire vessel. This translates into segmentation, which is networks, least privilege, and fault isolation. We also want systems that act like an immune system, constantly sensing anomalies, automatically quarantining compromised components. And finally, it spans the entire software development lifecycle, encompassing planning, designing, coding, testing, and deployment, operation. And then we have threat modeling at a design code, review and analysis during development itself, and we can perform pen test during release and design monitoring in the production so that we do not have any weak links, no blind spot. It's essential to think like an adversary to intercept attacks and apply engineering discipline to make resilience the default. With that foundation set, let's look at the cost of not doing this, rising price of insecure system. Before we dive into threats and defense, let's pause here and understand what really is at stake. Breaches are more expensive than ever. According to IBM and others, the average cost of a data breach hits $4.45 million in 2023, the highest ever recorded. This includes direct cleanup and notification cost, as well as lost business and reputational damage. In sector like healthcare, the average topped $10 million per incident. At the same time, the scale exposure is staggering. in 2024, the 35 most significant breaches alone resulted in the leak of 5.4 million records, and privacy fine exceeded $3 billion. That's personal data, trust, and brand equity being lost on a massive scale. The common denominator here is people, approximately 74% of breaches are attributed to human error or social engineering. One click on phishing, or one cloud configuration, one admin forgetting to lock door a bucket, and suddenly an attacker has a foothold. And these aren't just digital consequences. We have ransomware taking pipelines of pipelines failing, creating fuel shortages, hospitals breaches that force ambulance to divert mid-route. Insecure system can compromise critical services and pose a risk to human safety. The message is clear. The cost of insecurity is unsustainability. That's why we cannot rely on patching after the fact. We need security design and system from the starting. So how are attackers actually getting in? Let's look at 2025's data. So now let's talk about software development most often, where software development security most often fail. Insecure design from day one, which is one cost. If we skip that model and security requirement early, flaws get baked into our architectures. Dependency and supply chain risk. Every application shipped with dozens of open source libraries. If we do not keep them up to date, we inherit other people's vulnerability into our system. Pipeline and tooling attack. If CI/CD environment is compromised, attacker can slip in malicious code before we even realize. And then we have misconfiguration and deployment error. Things like open cloud bucket or default credentials are still among the top breach causes. Human factor in design. Features built without considering abuse cases, like an API without rate limit, become easy entry point. The common thread. These weaknesses are preventable, but only if we shift security left into the earliest life cycle of software development. So what does that look like in practice or in practical? Let's walk through how we can build security in step by step. When we talk about designing like an attacker, we really talking about spotting the weak points in software development lifecycle, because risk creep into at every stage of it if we are not deliberate. At this stage of design, insecure decisions like skipping authentication on critical features or choosing a weak hash algorithm become part of blueprint. That's why OEPS added insecure to its top 10. If we do not do the threat modeling and review architecture early, we are building blind, and those flaws are expensive to underwind later. At implementation, attacker count on our shortcuts. Modern apps relies on hundreds of open source libraries, and everyone is potential weak link. Think of Log4j. One flaw triggered a global scramble. In 2023, there were 2.1 billion downloads of vulnerable components, despite 96% having a fixed version available. Attackers know we're often slow to patch. That's why practice like SBOM tracking and software composition analysis matters most. At the build and pipeline stages, if you design like an attacker, you are going to go after CI/CD, compromise a build server or a developer account, and you can ship your own malicious code. That's precisely what happens in the code Kodvak and SolarWind incident. To defend, we need signed builds, isolated runners, and strong access control, hallmarks of engineering discipline. Finally, deployment and configuration. Attacker loves misconfiguration because they are easy wins and open storage bucket, our default admin password, our sloppy firewall rule. That's a free pass. In 2023, one misconfiguration bucket exposed emails and SSNs from multiple companies. We counted that automated infrastructure as a code, scans and insecure defaults baked into templates. The key takeaway here is design like an attacker means intercepting how flaws appear in each phases. And build like engineer means embedding controls and automate so that flaws are shut down early. Do that, they do that constantly happens, and they do not just close cracks. You raise the cost for attackers and lower your own cost to fix it. So far, we have seen how design, choose, shape become outcomes. And now I will request Ankit to take it over and walk you through the engineering half part and how testing, architecture, and resilience practice make system stand up even when attacker gets in. Over to you, Ankit.
Thank you. So Yep, thank you. Now let's shift into the engineering side and talk about the architecture. Here the goal is straightforward: limit the distance an attacker can move through or gain an entry. The first strategy is micro-segmentation. In the past, the flat networks meant that if you broke in once, you could roam everywhere. With micro-segmentation, each workload is assigned its own narrow trust zone, containing only the connection it truly needs. So for example, the authentication service lives on its own subnet, reachable only by the web frontend. And if malware lands on the user's laptop, there's simply no path to the finance database. Second is the strong identity, which is basically the zero trust. Internal IP addresses are no longer a free pass. Every API call, every service-to-service request must be authenticated and authorized with strong identity, service accounts, certificates, tokens, even MFA for sensitive actions. Combined with that with the least privilege, you shut down the lateral movement. If one service is compromised, it can't automatically talk to another without the explicit permission. Then we have the compartmentalization. Think of it like a ship with watertight compartments. One breach doesn't sink the vessel. In software, that means isolating the components. If users upload files, process them in a sandboxed container, not in your production runtime. Keep them in your keep your web servers, app servers, database servers separated with the narrow, well-defined interfaces. Then we have the last is the, the second last is the least privilege, which is basically underpinning all of these. Users, services, and processes should run within the bare minimum rights. If a web app only needs to read certain tables, don't give the database admin access. In cloud environment, that means fine-grained IAM role, also called as RBAC. It's already there from the 5-10 years, but we don't follow that. At the OS level, that means accounts with minimal file and directory permissions. And finally, the safer technology choices, the languages like Rust and Go, eliminate the entire classes of memory bugs, frameworks that validate the input validation by default, reducing the role of the odds of a small coding mistake. Then the bottom line, the design choke points, the compartments everywhere, segment the network, enforce identity at every hop, sandbox the risky process, run the least privilege, and choose safer tech. So architecture isn't just about the walls and the compartments. We also need to design for failure. So system limp rather than collapse when something goes wrong. So up to now, we have talked about keeping attackers out and containing them when they get in, but building like an engineer also means planning for the day when something does break. Attacks will happen. The goal is to bend without breaking. The first principle is designing for failure. This comes straight from reliability engineering. Assume that servers, services, and the network links will fail or be attacked. If a DDoS floods one region, redirect traffic to another, and make sure critical services are fail-safe, not fail-open. For example, freeze the risky transactions or on anomalies while the rest of the system keeps running. Next is the fault isolation and bulkheads. The circuit breaker pattern ensures service A doesn't hang just because service B is down. Rate limiters keep API being overwhelmed, whether by a bug or by a denial of service attack, so issues stay local and don't cascade. Then there is immutable infrastructure. Instead of patching the hacked servers, replace them with the hardened golden images and automation. You can build from a clean state in minutes. It's faster, cleaner, and removes the hidden malware very early. Backups still matters, but they must be isolated so attackers can't encrypt or delete them. An isolated recovery environment is like a digital wall cut off from daily system. Finally, the chaos engineering for security. This is a new buzzword launched in the last 2 years. Intentionally simulate failures or breaches. What if a critical security service is shut down? What if credentials leak? Do we detect any unusual logins promptly? Then these control environments actually provide the confidence that defenses and recovery process remain effective even under pressure. So in short, resilience means a system can contain damage, recover fast, and keep essential functions running. Now let's take a step further. What if system itself could detect, respond, and defend against the threats in real time? That's what the self-defending mechanism comes in. So far, we have focused on making systems hard to break into and resilient if something fails. Now let's go further. What if system could actively defend itself in real time? The first layer is continuous monitoring with anomaly detection. Instead of just matching known signatures, we teach the system what normal looks like and flag anything that's not. Think of a database that handles typically 100 queries a minute, suddenly spiking to 1,000 queries trying to dump tables, or an account constantly logs into from Texas suddenly shows up in Russia, accessing the HR files. Tools like UABA, user entity behavior analytics, works like a nervous system, alerting when something feels off. Detection isn't enough. Automated response is also critical. When compromise is apparent, speed matters. So if malware shows up on a machine, quarantine it instantly. If a cloud server behaves suspiciously, isolate it from the load balancer. Next is the deception technology, digital tripwires. We plant fake credentials, decoy servers, or bogus admin shares that no real world touch. If an attacker stumbles into them, alarms triggers immediately. It forces attackers to second guess everything they find. Then we have RASP, which is runtime application self-protection. It brings defense into the application itself. If someone attempts SQL injection or command execution, RASP detects and blocks it in real time. Finally, the baseline integrity monitoring. The system knows exactly what its critical files, binaries, or configs should look like. If something changes, such as tampered executable or disabled encryption, it flags the issue or rolls back to the clean state before the damage spreads. Together, these mechanisms make a system active in its defense, detecting, responding, sometimes neutralizing threats automatically, instead of relying on humans to catch everything. But there is a new force multiplier in this story, which is AI. Now we'll look into that part. 1 second. Yeah. So AI has become a massive part of cybersecurity, and it's truly a double-edged sword. On the defense side, AI is transforming threat detection. Traditional monitoring inundates analysts with thousands of alerts, most of which are noise. Machine learning can baseline what normal looks like and flag the anomalies. For example, if a database never sees bulk queries at 3 a.m., but suddenly thousands appear, AI will flag it. This is where AI shines, spotting slow, subtle intrusions humans might miss. AI also accelerates the incident response. In 2023, we saw the rise of security co-pilots, AI assistants trained on cybersecurity data that they can stitch together logs, identify what happened, likely happened, which systems are impacted, the blast radius, and the recommended next steps. IBM found that the organizations using AI and automation detection can contain breach 100 days faster on an average. So it's also changing the vulnerability discovery. AI can scan code for insecure patterns, flag dangerous API calls, and even suggest fixes. So integrated into IDEs, it's like spell check for security, warning a developer in real time and even helping the developer to automate certain parts of threat modeling. But we can't ignore the attacker side. Gen AI is already crafting more convincing phishing emails, probing cloud environment for misconfigurations, and mutating the malware to dodge protection. We are seeing proofs of concept for AI systems that can autonomously hunt for 0 days. The threat landscape is becoming faster, more adaptive. It's an arms race. So the upside is the companies that fully invest in AI-driven defenses, they say the real payoff. Breaches cost on average $1.76 million less what AI and automation are in place doing. So incidents are being detected earlier, contained more quickly, and often prevented altogether. Then the AI is also being used by attackers, so defenders have no choice but to operationalize is so responsibly with guardrails and human oversight. Otherwise, we give you but speed, and this race, speed is the matter of survival here. So with AI in the mix, the questions become how do we future-proof our systems? We are not constantly reacting, but steadily raising the bar. This will we go next. So let's talk about the how to future-proof our system so that design like an attacker, build like an engineer is in today's practice, it's built to last. First, build a security-first culture. Technology won't matter if people treat security as an afterthought. From leadership to developers, security must be viewed as an integral part of security, the quality. Every design should answer, how do we secure this? Next is the adopting the zero trust in stages. You don't flip a switch or you start where you don't boil the ocean and all together. You start where it matters the most, protect the customer data, enforce MFA everywhere, and then gradually expand the least privilege and continuous verification across networks, devices, and behaviors. Third is the secure the supply chain. Attackers love one supplier, many victims. Maintain an SBOM, update dependencies promptly, vet vendors for their practices, harden build pipelines. We have seen the risk in the wild. The SolarWind example was already given, Kaseya and MoveIt is Isabel. The fourth is the leverage AI and automation wisely. Use AI to spot anomalies, accelerate the investigations, and automate the first response. The scale of threat demands machines, but the judgment still belongs to us. Finally, commit to continuous improvement. Threats will shift, quantum may loom tomorrow, regulations may change next year. Update your threat models, run pen tests, red team exercises, and study breaches in your industry before this happens to you. The principles doesn't change. Least privilege, defense in depth, layered resilience, but how you apply them is a must constantly evolving theory. Transitioning, so let's wrap this up with all the key takeaways and a practical 30, 60, 90-day action plan before you can start immediately. First, design like an attacker. That means proactive shifting security left, map abuse cases, threat model features, and bake in security defaults before code ships. Second is the build like an engineer. The 24 and 25 threat landscapes demands it. Attackers are faster, wiser in targeting things we used to overlook. Your CI/CD pipeline, your help desk software, not just your firewall. Third is the most breaches are preventable. They often come to basics, no MFA, default configs, and missing validation in code. If we analyze real incidents and ask what simply could have prevented this and then actually implement it, we dramatically reduce risk. Sorry. Next step is your 90 days, 30, 60, 90 days plan. First is to make MFA as a universal and the baseline. 60 days to segment at least one high-value service, enforce short-lived service credentials, and add drift detection for critical configs. Then in the last, you run a red team exercise against the app, rehearse a clean rebuild from golden image, and publish your secure coding checklist as an organization standard. So each improvement builds momentum towards the system that defends themselves. Finally, security is not just a one-time project, it's a posture. The vision is basically optimistic. By designing the attackers and building like engineers, we make incidents rare, we limit their impact, and we keep enterprises running smoothly. Before we wrap up, I've included a few key resources that you can explore after today's session. These cover industry perspectives, research findings, and practical frameworks on secure by construction principles from leading organizations. I encourage you to review them, share them with your teams, and see how these ideas can be adapted to your environments. Thank you for listening. We are coming from Dallas for today's session. You can connect with us on this LinkedIn if you want to.
Anyone have any question? All right, so I think we can wrap it up. If you have any follow-up question, please feel to ping us directly on LinkedIn. We are good to coordinate afterwards as well. Thank you.
Thank you.
Thanks, everyone.